Hi, today in this video we will learn how to conduct a simple linear regression in R. For this we take an inbuilt data set in R with the name faithful. So I'll just invoke that particular data set. Let us have a look of the contents. So I write head of faithful, which will show me the first 6 entries of this data set. So there are two variables here, one with the name eruptions and other with the name waiting. Waiting is the explanatory variable that shows the waiting time or the interval between two consecutive geysers. Geysers are some catastrophic events that occur in USA. So waiting here denotes the interval between two consecutive occurrences of geysers. Now, eruptions. Eruptions is the dependent variable which captures the lifespan of an geyser after it has occurred. So, what I want to do is to find out a simple linear regression model that helps me to understand the relationship between eruptions and the variable waiting. So the first idea is to estimate the simple linear regression, and that can be done in R by the function called LM. So how do I do that? Say eruption.lm is the name of the variable where I'm capturing the result of the linear regression model is equal to LM eruptions regressed on waiting. Eruptions is the dependent variable and waiting is the independent variable, comma, the name of the data set is faithful. So the linear regression model has been fitted and we can look at the result. So the coefficient values which the model has received is intercept is -1.8 and the coefficient of the explanatory variable waiting is 0.07. Suppose now, after having fitted the simple linear regression, what we want is to find out the value of the dependent variable given the value of the independent variable. Say I have the value of the variable waiting to be equal to 80 and I want to find out the corresponding value of the variable eruptions from that equation. So how can this be done? We first save the value of the explanatory variable what we want to find out. So suppose I write new data is the variable where I'm trying to store the value of the given explanatory variable. So I write new data and I save it as a data frame as waiting is equal to 80. Say this is the particular value which I have been given. I want to predict the value of the dependent variable eruptions after having fitted this simple linear regression model. So how do I do that? So with the predict function in R, predict eruption.lm, I want to predict the value of eruption.lm given that the value is 80 for waiting. So I write comma new data. So new data invokes the value of 80 for the explanatory variable waiting. That gives me the value 4.17. That means when the value of waiting is equal to 80, the predicted value of the eruptions is 4.17. This is inferred from the fitted linear regression model with the coefficients being -1.8 and the waiting time being 0.07 respectively. Okay. Now, let us come to another question. Say for this model, I want to find out the coefficient of determination. Now, coefficient of determination is what? It gives me a fit, a measure of a goodness of fit, of how good the model fitted is actually. So, how do I find that out? I know that the summary of the linear regression fitting contains all the necessary metrics and I can infer it from there. So let us first have a summary measure. I write summary of eruption.lm that gives me a summarized version of the results of the eruption data. Here I have coefficients, I have the residuals and a few important metrics like the residual standard error, the multiple R-square, adjusted R-square and the F statistic along with the p-value. So the objective what I want to find is the R-square value. So I can do that by writing summary eruption.lm dollar r squared. So among these important information, I want to find out the value of r squared. So I quote it with a dollar. I write summary of eruption dollar r squared. That gives me 0.811460. That is approximately 81.14%, which is a significant fit. That is a good fit. All right, so now we know the coefficient of determination for the fitted model. Let us come to the significance test for this linear regression. How do we do that? See, with the coefficients and their p-values, we can find out the test of significance and know whether the explanatory variable is significant in explaining the variations in the dependent variable or not. And what is the idea about it? Okay, so the p-value here, if we notice, for beta naught and beta 1 is less than 0.05. So it is less than 0.05 means that we can reject the null hypothesis that beta is equal to 0. These are the p-values. This is the p-value set for both of them. So as both of these values are less than 0.05, we can reject the hypothesis, the null hypothesis that beta is equal to 0. Hence, there is a significant relationship between the variables in the linear regression model. That means weighting, the explanatory variable weighting, has a significant effect in explaining the variations in the dependent variable named eruptions. So with this, we've been able to conduct a simple linear test of regression. Now let us come to the point if I want to fit a confidence interval for this linear regression. Say the question which I have in hand is that the waiting time is say 80 minutes again, and I want to fit a 95% confidence interval for the mean eruption duration given that the waiting time is 80. So what is a confidence interval? A confidence interval, what it does is, for a given value of x, it finds the interval estimates for the mean value of the dependent variable. Mind you, it is different from a prediction interval, which we'll see shortly. So in the case of a confidence interval, what we do is to find the estimate of the mean value of the dependent variable given the value of the explanatory variable. So say that the explanatory variable value is 80. I want to find out the estimate of, or the confidence interval estimate for the mean value of the dependent variable. And how can this be done? First, I save the value, the given value, in some variable. Say, as I had done before, say new data is equal to data frame weighting is equal to 80. Then I want to predict the value of eruption.lm given this value. So I write is equal to new data, interval is equal to confidence. When I explicitly mention that the interval which I am trying to estimate is a confidence interval, it will give me the confidence interval, the 95% confidence interval estimates. So the result is as follows. See, the fitted value is 4.17 and the lower and the upper bounds, the 95% confidence interval bounds, are 4.10 and 4.24 respectively. That means the 95% confidence interval for the mean value of the dependent variable, given that the waiting time is 80 minutes, is between 4.10 and 4.24. Its estimate has been found to be 4.17. So with this, we've done the confidence interval. Now let us come to the prediction interval for this linear regression. Say again, the question is to find out the prediction interval given a particular value of the explanatory variable. A prediction interval, in contrast to the confidence interval which we just saw, what it does is to find the interval estimate for the dependent variable y for a given value of x. So the difference is to be noted. The prediction interval finds the estimate of the dependent variable y, whereas the confidence interval finds the estimate for the mean of the dependent variable y. So Suppose for the same case again, if I have the waiting time fitted as 80 and I want to find the prediction interval for this, I write the same equation, predict eruption.lm, new data, interval is equal to predict this time. So this gives me the fitted values and the lower and the upper bounds for the predicted interval given that the waiting time is 80. So this means that for the case when the waiting time is 80 minutes, the 95% prediction interval for the eruption, which is the dependent variable, is 4.17, and the lower and the upper bounds are 3.19 and 5.15 respectively. So with this, we've seen a number of things. First, we had a small data set in hand. The first idea was to fit the simple linear regression for it, and given the value of any explanatory variable, we can find the value of the dependent variable from that particular regression fitted model. We've also seen how to find the coefficient of determination at what it means. We've done the test of significance for this linear regression by looking at the p-values and seeing whether it lies, it is more than 0.05 or it is less than 0.05. Then we fitted the confidence interval and also the prediction interval and understood the difference between both of them. So this is how a simple linear regression is fitted in R. Thank you. Hi, today in this video we will learn how to fit a multiple linear regression in R. For this, we take a data set which is inbuilt in R with the name of stat laws. So first let us invoke the data set. The name of the data set is stat laws. And have a look of the data set by writing head of stat laws. That gives me the first 6 entries. So here the stack.loss is the dependent variable that finds the stack loss. This is for some chemical plant where the explanatory variables that enter into the model are airflow, water temperature, and the acid concentration. These 3 explanatory variables enter into the model and predict the stack loss for this chemical plant. So what we want to do is to find a relationship between these 4 variables. So the first is to estimate a multiple linear regression equation. So in R, that can be done with the LM function. We've already seen in the case of a simple linear regression how the LM function fits a model. Here also with the same LM function, we can estimate the multiple regression equation. So I write, say, stack clause dot LM is equal to LM, the linear model, where I'm regressing stack.loss on the variables air.flow plus water.temp plus acid.concentration. So this is the dependent variable stack.loss, and these 3 are the independent variables, comma, the data is stack loss. So this is the equation. So I can have a look of the fitted multiple regression equation like this. Sorry, it should be stackloss.lm. So with this, we have a look of the result, what we found from fitting of the multiple regression equation. The intercept is minus 39.9 and the coefficients for these 3 explanatory variables are 0.71, 1.2 and minus 0.15 respectively. Now, suppose the question which we have in hand is that after we fitted this model and found the values of the coefficients, I have the given values of these 3 explanatory variables. and for that I want to find the corresponding value of the dependent variable. Say I have three values given for the explanatory variables and I want to find the value of the dependent variable from this fitted estimated multiple regression equation. So I save those values in a variable. Say new data is that variable which is storing these as a data frame. So I write new data dot data frame is equal to, given the values are airflow is equal to say 72, comma, water dot temp is equal to say 20, and acid dot concentration is equal to 85. These are the values given, and for the corresponding values of these explanatory variables, I want to find the value of the dependent variable using this fitted multiple regression equation. So how do I do that? With the same function called predict, how we had used in the previous case. I write statloss.lm using which values? The values which are contained in new data. So I write comma new data, and the predicted value which I receive is 24.58. That means after having fitted the regression equation, we see that if the values of the explanatory variables are 72, 20 and 85 respectively, the corresponding value of y, the corresponding value of the stack loss is 24.58. So with this, we've been able to predict the value of the dependent variable given the values of the independent variable. Now suppose I want to find out the value of the multiple coefficient of determination for this case. So as we all know, when there's a multiple linear regression, the coefficient of determination is called the multiple coefficient of determination. How do we do that? As we've seen in the previous video, for the case of a simple linear regression, the same thing happens here. We can write summary of stack loss dot lm dollar r squared, and we get the value to be 91.35%. That means the fitted model has an r square value of 91.35%. Suppose now we want to find the value of the adjusted coefficient of determination here. The adjusted coefficient of determination can be found in the same way by writing summary of stack loss.lm dollar adjusted adj dot r squared, and I get the value to be 89.83%. The test of significance for this case can again be done by observing the values, the p-values of the fitted coefficients, and that can be seen from the summary function. So I write summary of stack loss.lm, and I get these p-values for the corresponding betas. So I see that all the p-values here are less than 0.05, which means that they are all statistically significant in the multiple linear regression model and all significantly explain the variations in the dependent variable. Similar to the previous case where we tried fitting the confidence interval and the prediction interval, we'll try to find out the confidence interval for this multiple linear regression case. What we do is to first fit the values of the independent variable. So say new data is equal to data dot frame of, the values are air dot flow is equal to 72, say water dot temp is equal to 20, and acid dot concentration is equal to 85. Then I predict these values stack loss.lm using the new data values, keeping the interval is equal to confidence. Thus, the fitted value is 24.5 and the lower and the upper bounds are 20.2 and 28.9 respectively. With this, we fitted a 95% confidence interval. The same can be done for the case of a prediction interval where I just have to replace this with predict and the same values of the new data enter, and we find that the predicted value is 24.5 and the lower and the upper bound values are 16.4 and 32.6 respectively. So we've seen the fitting of a multiple linear regression, the estimation, the coefficient of determination, the adjusted coefficient of determination, the significance test, the confidence and the prediction interval in R. Thank you. Hi, today in this video we will learn how to treat missing values in R. For that we'll take an example of a data set known as algae, as we've done in the previous video, by loading the library of a package known as dmwr, and then we invoke the data set by writing data of algae. See the first 6 entries by writing head of algae. This data primarily has 11 explanatory variables, 3 are categorical and the remaining 8 are quantitative. The dependent variables are from A1 to A7, where A1 is the dependent variable where we will focus on, and we will try to analyze the model taking A1 as a dependent variable. So there are a lot of missing values in this data set. There are some any, they are denoted as any means not available values. So first we would like to see how many rows are there in the data set where the values are not present. So for that I write n row. Algae is the name of the data set. Not of complete dot cases algae, comma, and then close the brackets, gives us 16. So in this entire data set there are 16 rows where there are any values present. So how do we treat these any values? There are various techniques to do so, and we'll shortly say how to do that. Say if I want to find out the number of rows where the any values are a certain proportion of the total number of the explanatory variables. How do I do that? Say I want to find those row numbers which have more than X% of the columns containing any. So let X be 20%. So how do I do that? So I write many NAs algae, comma, 0.2. That will give me those row numbers which have more than 20% of their columns with containing any values. So it gives me 62 and 199. That means row number 62 and row number 199 are such that more than 20%, that is more than 1/5 of their columns have any values. So I may want to delete these particular rows such that the data set does not comprise these particular rows because they have a lot of any values. So I write algae of algae minus many NAs of algae, comma. So now if I see number of rows for algae, it is 198. So in total if there were 200 rows. Now row number 62 and 199 have been deleted, therefore the number of remaining rows is 198. So this is how one can treat the any values, by having techniques such that if they exceed a certain proportion of the total number of columns, I want to delete it. So say another user may want to set it as 0.5 or 0.6 or any fraction that would serve as a threshold, such that if the number of NA values are beyond this, I would like to delete it from my data set completely. The other method could be to fill in these unknown values by using the most frequent values. Now how do we find what are the most frequent values or the most probable outcomes? One technique is to find those and to fill the unknown values with some statistic that becomes a measure of a centrality. So how can we do that? It will basically depend on what situation we are, because in certain cases the frequency or the most probable outcome is given by the mean. In some cases it is denoted by the median or the mode or anything else. So we have to see what could be the most important or the most significant metric which will help us to fill those any values. Now suppose we have an example. Suppose I know that row number 48 of this data set does not have the value of the variable called mxph. So mxph for the 48th row is an any value. So we've already seen in our exploratory data analysis video that mxph is nearly normal.
So if I know that a variable behaves nearly normal, I can use mean as one of the measures of central tendency that will be used to fill this missing value. So for that, I can write algae of 48 because it's the 48th row, and I want to fill in the variable mxph will be filled with mean of algae dollar mxph comma na dot rm is equal to true, because the na values are supposed to be removed. So that I have successfully done. That means for the 48th row, the value taken by the variable mxph will be the mean of the values of the mxph. So there is another function known as the central imputation function also, which can do this, and we'll shortly see how we can make use of that in order to fill the missing values. And another technique could be by finding or to explore the correlation between variables. So if I know that there exists correlation between variables, we can discover that a certain variable is highly correlated with another variable, and using this speciality we can use the correlation function to fill in any blank to fill in any value or any missing value that is present. So suppose for the sake of simplicity, I want to first find out how the correlation between all these explanatory variables are. So if you see, from the 4th till the 18th variable, I have all the explanatory variables. So I would like to first see how the correlation matrix is for all these explanatory variables. Now how do I do that? In R, we can do this by this function called simnum correlation algae all the rows from the 4th till the 18th column, comma, use is equal to complete dot observations. That means with this function, what I can see is a correlation matrix between all these variables. So I see for all these variables, right from the first 3 were qualitative variables. So beyond that, from mxph up till the last variable, I have that is for the 4th till the 18th variable, I have plotted the correlation matrix. Now from this correlation matrix, if you decipher these symbols and you find out their values, you see that PO4 and OPO4 have a value denoted by this asterisk that carries a correlation value of 0.95. That means there is a high correlation between the values OPO4 and PO4. They have a high correlation value that is 0.95. So using this also, I can try to fill up any values which is present in the data. So suppose there is any place where PO4 value is missing. Now because I know that PO4 is correlated with OPO4, I can use the value of OPO4 in order to fill the missing value PO4. How do I do that? Before that, I'll just reload the data because we've already treated it and it has changed now. So I write data of algae, and algae is equal to algae minus many NAs algae. Yeah, so it has successfully deleted those two rows, the rows number 62 and 199, because they had a lot of missing values, and it is not harmful if we delete them. Now I run a regression between PO4 and OPO4 because I know that they are correlated, where data is equal to algae. It gives me this equation by regressing PO4 on OPO4. The intercept is 42.87 and the slope value is 1.293. Thus, PO4 will be equal to 42.897 plus 1.293 times the explanatory variable OPO4. Therefore, with this, now that I know the value of OPO4 for any row, I can use this linear equation and fill up the value of PO4. So, say algae, if I know that the 28th row has a missing PO4 value, so I write algae 28, that 28 denotes the row number, PO4 denotes the column number, will be equal to 42.897 plus 1.293 into algae of 28 comma
OPO4. So with this, I have constructed a linear equation that will take in the value of OPO4 existing at the 28th row, and with this it will form a linear equation that will be used to fill up the value of the 28th row PO4 value, and this I have successfully done. So if there was a missing value in the 28th row for the PO4 variable, that has been successfully fitted. Another way could be to find the similarities between a few cases. So suppose I find that there are two samples and they are similar to each other, and one of them has an unknown value in some particular variable. Then there exists a high probability that this value is similar to the value of the other sample. And how do we do that? We'll just have a look. That can be done by the mathematical concept of the Euclidean distance. So for this, I will again load the data set, say data of algae, because it has again been treated so many times, and I again try to delete algae is equal to algae minus many NAs algae, comma. With this, I've been able to delete the row number 62 and 199 for the reasons we've already discussed. So suppose I want to find the 10 most similar cases for any sample with some unknown value in a variable, and we will use these 10 similar values in order to fill the values of another unknown variable. So suppose I have two samples in my hand. In one of the samples, a particular variable's value is missing. However, in the other sample, the value of that variable is present. So I will take the 10 most similar cases from that sample and use those 10 cases to fill that unknown value, that missing value. This function is known as the KNN imputation function, and what it does is to use a weighted average of the values of the neighbors. So if I have, say, 10 neighbors, it will take a weighted average of those 10 neighbors values and use it to fill that NA value which is present in my data set. And logically, as the distance between the point of consideration and the neighbor value is increasing, it will have a lesser weight. So the closer the neighbor, the more weight it will have. So that is how the logic goes. So I write algae is equal to KNN imputation algae, comma, K is equal to 10. So K is equal to 10 is setting the parameter that I want to consider 10 nearest neighbors in order to fill the missing value, and that is done. So now if I write algae of KNN imputation algae, K is equal to 10, and I want this time to purposefully use a certain other metric other than the mean. So by default, this KNN imputation takes a weighted average of the 10 nearest neighbors. Suppose in a particular program or for some prospect, I want that instead of taking the weighted average, it should take the median of those 10 neighbors. So I can explicitly mention here that method should be equal to median. So instead of taking the weighted average, this KNN imputation function will take the median of those 10 nearest neighbors and use them to fill up the missing NA value. Hi, today in this lecture we will see how to treat outliers in R, taking the example of a data set with the name rivers. So we load the data set and see the components. This data set comprises the length in miles of a few rivers, say 121 rivers of North America. The length of this data set is 141. So let us have a pictorial representation of how the data set looks like. Histogram. So this histogram shows that the data set is a highly skewed one, and there are a lot of entries here. A number of rivers here which have lengths much different from the rest of the data set. So we see a major portion of the data set lies between the river lengths, say 0 to around 1500, 1700 miles, and there are very few number of rivers beyond this value. So this data set is treated with the problem of outliers, and we'll see how to treat it. So for a better version of the data set representation in terms of the pictogram, we'll see the box plot by writing box plot of rivers and keep horizontal version is equal to true so that we have a horizontal look of the data set. So if you see, the most of the data set lies between 0 to around 1200 miles, and there are very few number of entries which are beyond 1200 miles. So how do we treat these outlier values? So you see these circles represent the outliers present in this data set. So from this representation, we see that 1200 or say around 1200, 1300 could be the value beyond which there are a lot of outlier values. So how do we treat that? So we will create another data set, say river1, RIV1, which will contain a subset of the original data set where all the river values are less than, say, 1250. So we keep 1250 as the limit beyond which I am treating the remaining values as outliers. So all the rivers where the length is more than 1250 are treated as outliers. Now I'll create a box plot of these values, river 1, comma, again going for the horizontal version, horizontal is equal to true, and see that the number of outliers have considerably decreased. So in the previous one we had a number of outliers, but now they have reduced to some around 4. And then again I can repeat the same exercise here by keeping my threshold value as around say 1050 or about, and keep 1050 as my limit beyond which the values will be considered as outlier values. So say river 2 will be the set of all those rivers where rivers is less than 1050. So all the rivers which have sizes beyond 1050 are treated as outliers. So Riv 2 is a new data set, and now I plot the box plot of Riv 2, keeping again horizontal parameter is equal to true, and see that the number of outliers have been removed. So now this data set has no outliers present in it. By treating the data considerably over a period of time, reducing the limit to which the outliers could be extended to, we found that all the rivers beyond 1050 miles of length have outliers. So now with this small exercise, we've been able to remove the presence of outliers from the model. So Riv 2 becomes the new data set with which I can do the entire analysis, because that does not contain any outliers. So now if we see a histogram of Riv 2, it will be a fairly considerable one, and a lot of values have been removed, and now it has become a much more equitable distribution than the previous one. That's it. Thank you. Hi. Today in this recording, we will see how to conduct a logistic regression using the software R. So I have a small data set. We'll take it as an example and learn how to conduct the logistic regression in R. So there's an inbuilt data set in R with the name called empty cars. So we'll just use it for an analysis. So I just invoke that data set and keep it ready. Empty cars is the name of the data set. What we are trying to do in this data set is to find out the type of engine which this vehicle has. So the dependent variable has a name which is VS, a V engine or a straight engine. That is why the name of the dependent variable is VS, and we will try to regress VS on the weight of the engine and the displacement of the engine. So basically VS is my dependent variable, and the independent variables are weight denoted by WT, and another independent variable is displacement, which is denoted by DISP. So VS is my dependent variable. It is categorical in nature. That means VS will take a value either 0 or 1. It is a binary outcome. Weight and displacement, however, they are continuous variables. So because in this case the dependent variable is binomial, I'll have to fit something called a logistic regression. As we all know, we'll go about doing that. Also, we want to find out that after fitting the logistic regression, if I have a certain value of weight and a certain value of the displacement, I have to find out the probability of getting the value of VS. So how do I do that? We'll just go about checking this. So the first is to fit a logistic model. In R, the fitting of the logistic regression model happens with the function called the GLM. So let us do that. Say model is the name of my variables, is GLM, formula is equal to VS tilde weight plus displacement, comma, data is equal to empty cars, comma, family is equal to binomial. Just have a look at the format. Model is the name of the variable in which I am storing it. Weight and displacement are regressed on the dependent variable, which is VS, that is binomial in nature. We want to find out how they are related. So we fit a logistic regression. The data set has the name empty cars and we are fitting a binomial family. So next, when I want to see the results, I write model and I get the value of the intercept and the coefficients of the weight and the displacement. Here it is to be noticed that my dependent variable is categorical. What we are running is a logistic regression. Therefore, these coefficients are the values of the logits, which is log of odds. We'll come to the interpretation in a moment. Let us see a summary of the result. So I write summary of model and then I find the result is something like this. So this is the regression equation which I have run. These are the deviance residuals, the coefficient values, and the null deviance, the residual deviance, and the number of Fisher scoring iterations. We'll just come to their interpretations and I'll let you know about it. Before that, a simple question arises is that after this fitting, if I want to find the probability that a vehicle has a VS is equal to 1. So VS, as I told you, will take a value either 0 or 1. So VS is equal to 1 means that it has a VS kind of engine, and VS is equal to 0 means it is some other kind of engine. So I want to predict the probability that a vehicle has a VS kind of engine, given that the weight is say 2100 and the engine displacement is 180. So how do I do that? First of all, I create a variable that stores these values of the explanatory variables. So say I create a data frame with these values. I write weight is equal to, given the weight is 2.1 and the displacement value is 180. So with this, I have stored it. Now what I want to do is to predict the value of the probability that VS is equal to 1, given that the values of the explanatory variables weight and displacement are 2.1 and 180 respectively. So I want to predict the value taken by the model, given that the values are stored in new data and the type is a response, because this is a kind of a categorical outcome. So I get the value equal to 0.23. That means the interpretation is that when the weight is 2.1 and the displacement is 180, the probability that a vehicle comes into the VS category is 0.24. That means the probability of any vehicle having a VS engine is 0.24. So this is a simple example of how to fit a logistic regression and how to use it for prediction purposes. Now we come to the more technical part of it, which talks about these values, the numbers, the coefficients, the deviance. As you see here, there's something called the deviance residuals. There's something called the coefficients. We should know how to interpret these coefficients. Also here, there's something called the null deviance and the residual deviance. Now what are these? So let us first start with the thing called deviance. Now what is deviance? In our case, we have a value of 43.86 on 31 degrees of freedom. This value is the null deviance. What is null deviance? Now null deviance is the value that shows how the response variable, that is how the dependent variable is predicted by this model, given that it includes only the intercept. That is, there are no explanatory variables in the model. There is only one variable, which is the dependent variable. that is regressed on the intercept only. So in that case, the value of the deviance is 43.86 and there are 31 degrees of freedom. Now, as the name suggests and as common sense implies, deviance is a value which should be as low as possible. So the more the deviance, the worse the fitting of the model is. So we should always have a model which has a low value of deviance. So from this we know that in case I try to fit the dependent variable on the intercept only, that is, I do not keep any of the explanatory variables in the model has a deviance of 43.86. So that is nothing but the null deviance. Null deviance means fitting of the model on the intercept only without keeping any explanatory variables. Now, there's something called the residual deviance. The residual deviance is the deviance of the model after including the explanatory variables. So we see that after including the explanatory variables, weight and displacement, the deviance has decreased from 43.86 to 21.4, and the degrees of freedom have fallen from 31 to 29. So because of including two explanatory variables, the degrees of freedom fall by 2, and as a result of which the deviance value has decreased. That means the model fitting for my case has become better. Earlier, the deviance without any explanatory variable was 43.86. However, after including two variables, the weight and the displacement, the deviance value has decreased to 21.4. That means the residual value has decreased by approximately, say, 22 units with a loss of 2 degrees of freedom. Now, we come to something called the AIC values. As we can see here, the AIC values is 27.4. Now, what is the interpretation of an AIC value in this context? The AIC stands for the Archaic Information Criterion, and what it does, it provides us a method to assess how good the quality of my model is in comparison with other related models. So, in case I have a number of models, say 4, 5, 2, 3 number of models in my hand, I want to find the best fitting model. I should choose the model which has the lowest value of the AIC. Now, in this context, it is not a very important number to make use of because here we just have one model. In other cases, AIC is a very important and a very significant measure because it helps us to find the best model out of a number of similar models. So in those cases, if I have a number of similar models and I want to choose one out of them, the criteria should be the AIC, the Archaic Information Criteria. The model with the lowest value of the AIC should be chosen and should be considered as the optimal model. So here in our case, our model had an AIC value of 27.4. Had we compared it against other models, all of those models have had different AIC values, and based on that, we could have found out the best fitting model. Now, how do we interpret these coefficients? These are the coefficients. I have regress the value, the Vs, which is the dependent variable, on two explanatory variables, weight and displacement. And the coefficient values which I have received is 1.62 and minus 0.03. So the first very evident thing which I can see is that weight influences the dependent variable positively and displacement affects the dependent variable inversely. So this is a positive relation, this is a negative relation. Now, as we all know, in the case of logistic regressions, the dependent variable which I have is logit, which is log of odds. That means when the interpretation, please be careful, the interpretation is as follows. When the weight of the machine or the weight of the vehicle rises by 1 unit, that is 1 pounds in our case, the log of the odds of Vs being equal to 1 rises by 1.62 units. So if I say that the log of odds is rising by 1.62 units, the odds will rise by e to the power of 1.62 units. So this is very simple, a little mathematical maybe, but the interpretation is straightforward. When weight increases by 1 unit, the log of odds of Vs being equal to 1 will rise by 1.62 units. That means odds will rise by a value of e to the power 1.62 units. Similar interpretation holds for the value displacement. For displacement, the estimate is minus 0.03. Now what does it mean? When displacement rises by 1 unit, the log of the odds of the value Vs being equal to 1 will fall by 0.03. That means the odds will fall by e to the power of minus 0.03 units. So that is how these estimates are interpreted. From the probability, the p-values, these p-values we can find out more on their nature as in terms of their significance, whether these variables, weight, displacement, they are significant or not in explaining the dependent variable. From the null deviance and the residual deviance, we have been able to find out how the deviance has decreased or changed after including the explanatory variables. Null deviance is when there are no explanatory variables in the model and the regression is done only on the intercept, as in there are no explanatory variables. And residual deviance is that what happens when there is an introduction of the explanatory variables. So with this, we've been able to show a simple case of a logistic regression. We fitted the logistic regression here with the GLM function. GLM stands for generalized linear models. With the GLM function, we've been able to fit the logistic regression. It is stored in the variable called model. So when I write model, I'm able to see all the results. The coefficients are visible. A summary of the model shows all the important metrics which I want to calculate. Also, after the fitting of the model, if I want to make use of it in terms of prediction, I can do that. Given the values of the explanatory variables, weight and displacement, I can find out the probability that Vs will be equal to 1. Vs is my dependent variable. So with that, I've been able to predict the value is 0.24. That means when the weight is 2.1 and the displacement is 180, the predicted value, the probability that Vs will be equal to 1 is 0.24. And then we've seen the implications and the interpretations for the coefficients, and that is how a logistic regression is run in R. Thank you.
In this video, we are going to build a logistic regression model that will predict whether the stock price will move up or down. So basically what we are going to do here is build a model, build a predictive model that will predict whether the stock price will move up or move down. So it's a stock price movement model. I'll take the ISLR data. So let me first run the library and let's see what's there in the data. So the library is ISLR, the data is S market. Okay, so this is a capital market data, so that's why it's called S market, stock market. Okay, so we've got the year and then the lag, the different lag. There are 5 lags for the stock price. So what do you mean by lag? Lag is nothing but the price of stock for the previous periods. So the lag of stock price for today's price is just the yesterday's price. That's the first lag. Day before yesterday's price is the second lag, and then 2 days before today is the third lag. That's the way we calculate the lag of stock price. Direction has the data for the stock price going up or down, and that's important because that's what we are trying to predict. So that's going to be the target variable for us. We've also got volume that will give us what is the volume of the trade that has happened. Alright, with this data in mind, so let's start building the model. Before that, let's see or let's understand the data a little more. What's the dimension of the data? We've got 1250 observations and 9 variables in place. Let's first see how the data looks like. So this is the data. We have got the different lags and then volume data, and we have got the direction up or down. So that's going to be the target variable for us, and it has got 2 values. So it's a binary data, the target variable is binary in nature. It has got only two values, so we'll use logistic regression to predict whether it's going to go up or not. Okay, so the idea is to find the probability of the stock price going up. Okay, so let's first do summary of the data. Now, finding out the descriptive statistic is very important, and it's important in any model building process is the primary thing. It gives us an understanding how the data is distributed, and that's what it is. So we'll also see the correlation of data. Okay, as expected, the correlation of the stock price is sort of correlated with the lags, its respective lags, and that's expected because stock price of today is correlated with stock price of yesterday and stock price of day before yesterday, right? So that's what we are also experiencing here. So that's quite obvious. So once we have certain amount of understanding of how the data is, we know what is our target variable and what are our explanatory variable, then we'll straight away go with modeling. Okay, now I'm not taking the training and test data as to, I'm not doing a sampling of dividing the data set into training and validation or holdout sample and then building model. We'll see what problem that one would face if you do not go ahead with that kind of sampling. Okay, and that way you will understand why sampling is so important, why it is good to build a model with one sample with one set of data points and then test your model with the holdout sample. So we'll do with the full data set and we'll see what exactly is the problem that you might face if you just use the the full data in order to build the model. So we'll use the GLM function, which is the generalized linear model, and logistic regression is part of the generalized linear model. Hence, we'll use the GLM. The syntax is pretty much same that you might have seen in logistic regression or in linear regression. We have got the target variable in the left hand side, and in the right hand side we have got the explanatory variables. So we have used the 5 lag prices of the stock price and then the volume, and the data that we have used is S market, the data that we just saw. Remember, so just one thing you remember here, we have not divided the data into training and test sample. We'll do that later, and we'll just see if you don't do that, what's the outcome. And the family of the model that we are using is binomial here. Remember, it's a binomial model because it has got the target variable has got only 2 values. Okay, so that's important. So you need to mention what the class or the family of model that you're fitting out from the generalized linear model. So let's run this. So I've run this. Now the results are stored in the variable fit, and let's do the summary of that. So when we see the summary of this variable, we've got so normally whatever you get in a logistic regression, you get that in your summary statistics. We have got the intercept and the slope coefficients. Okay, so these are the details for slope coefficients. So look at the estimate. Okay, and that's very important because that gives you the intercept and slope coefficients. So the intercept is minus 0.126. The slope coefficients are minus 0.07, minus 0.04 for lag 2, minus 0.01 for lag 3, and so on. So looking at the estimates, we can understand sort of the relationship between the movement of stock price with respect to the the lag variables and the volume. Okay, a negative relationship actually talks about sort of a negative impact, and the positive if the estimate is positive, then it is a positive impact on the on your target variables. Okay, one thing that is also important is looking at the p value. because that gives you the sort of confidence about your significance of variables. So what we'll do is that we'll just take the coefficients from the only the coefficients. Okay, so we have got these coefficients. So these are the coefficients. Now we can take these coefficients to an Excel sheet and use this coefficient in a logistic regression equation. I'm sure you are familiar with logistic regression equation. Use that equation and find the probability that the stock will move up. Okay, so the price will move up. That's, you can actually always get it done manually, but we can do it directly. We don't have to take this estimates values and do it manually. By just using the equation, we can directly predict the probability using this model. Okay, so how we'll do that? We'll use the predict function to be able to do so. And we'll store the probability values in what is known as the prob. We'll just define a variable prob, and you can give any name to it. So I'm just given prob, and the function predict will take the coefficients from the model that we just built now, and then the type is a response. Okay, so it is going to what is going to predict is nothing but the target variable along with the probability. So we all will get in the prob is the target variable, ups and down, and their respective probability. Okay, fine. Now let's run this. So we'll run this, and then let's see what exactly do we have in this particular variable. So we'll just print the first 20 observations, and let's see what are there. So now we can see we have got the probabilities for respective observations. Now you will get that for entire set of training data. Now remember one thing, we are doing this prediction only on the training data. So we have just used the same data for building model, and we are also predicting the probability with the same data. Ideally that should not be done, but for demonstration, for illustration purpose, I'm just doing it, and I'll show you what exactly is the problem, and we'll come to know that. So now we have, for each observation, we have got the respective probability of that happening. Okay, so in order to see whether our predictive model is doing a good job or not, we'll use some metrics in order to evaluate the performance of this model. So some of the commonly used metrics are confusion metrics and the accuracy ratio. Okay, so we can easily get a confusion matrix. So how do we get that? So we use we just create a matrix with 1250 observations. So that's is nothing but the total number of observation in our data set. We just create that with the value up, and if the probability value in the predict matrix in this vector is less than equal to 0.5, then we just assign it to be down. Otherwise it is up, because it's already there in up when we define itself, and every time it is less than 0.5 we call it down, right? And how is that, and why do we do that? Because the threshold point that we can take in order for us to classify the data into ups and down is 0.5. It could differ, actually. It depends on the situation we are dealing with. Some specific problems demands a different threshold value, but mostly we use 0.5 as the threshold. So any probability of greater than 0.5 is considered to be stock price moving up, and probability less than equal to 0.5, we just consider that as stock price moving down, and that's exactly what we have done here. Okay, so let's run this. Now let's tabulate the predicted value and the actual value. Now, our actual values for market up and down for the data that we have used for this 1250 observation, we have that in the data itself. So S market has the variable direction, and that has got the actual data. And pred that we just defined above will have the predicted values, right, ups and down. So let's tabulate and let's see what is the correct prediction and what is the wrong prediction. When you run this, now you can see here. Okay, so one second. So this is pred. So this is the vertical one is the pred, and the horizontal one is the actual data. Okay, so this is actual data. Here it should be actual, and here it's predicted. So now don't confuse with that. In the column sector we have the actual, and in the rows we have got the predicted. So actual down and predicted down, we have got 145 observation like that. Actual up and predicted up is 507. So we've got correct prediction of 145 plus 507. That's correct prediction. And so that's the diagonal matrix. The off diagonal matrix, off diagonal numbers 141, which is like the actual is actual is up, and the predicted is down. We've got 141, and the actual is down and the predicted is up. It is 457. Now we can see that the prediction is somewhat okay, but not that great, because we have got a lot of wrong predictions, right? So how do we get to know what percentage of data is correctly predicted and what percentage of data is not correctly predicted? And you can easily get that, right? How do you get that? We have got the the predicted data, and we have got the actual data, right, from the data set. So just take the cases where they are matching. If up is there in actual and up is there in the predicted, they are matching. Okay, and that's one pair of matching pair. If both are down, that's also a matching pair. If up is down and down is up, that's not a matching pair. So let's take the average of all the cases where it is matching with the actual is matching with the predicted. So if that is done, we just find it to be 52%. Okay, which is not very great. It's just slightly better than the random prediction. The logistic regression ideally should give better. However, we have just got 52% correct prediction, which is slightly better than a random prediction. So randomly, if you just toss a coin and predict whether it's going to go up or go down, you will get 50% times correctly. Okay, and 52% is just slightly better than that. However, the problem is that you can't trust this confusion matrix or the accuracy test. Why so? Because we have taken the data that we have used for model building purpose. So we have taken the same data for building model and used that same data for validating it, and that's a wrong way of doing it. Okay, the reason is very simple, because if you use the same data for validation purpose, it is most likely underestimate the error or underestimate the misclassification. So that's one thing you should know very well, that if you use the same data, the misclassification is always underestimated. Hence, it's always good to go with two sets of data which is completely disjoint. That means they are totally different. No single observation is common in training and test data. Build the model in training data and test it in the test data. So what we'll do is that we'll create two samples, training and test samples. So we've got the training data here. Data which is less than or before 2005, we'll just take that as a training sample, and we'll build that model and we'll test the model in the data 2005. So this is technically this is called out time validations, where your training data comes from a different year and the test data comes from a totally different year. So the training data is from 2001 to 2004, and the test data is of 1 year data, which is 2005. So we created a training sample. So it's simple to create. and then we create a test sample based on this. Okay, and then let's see the dimension of the test sample. So we have got 252 observations which belong to the year 2005, and that happens to be the test sample for us. Now we'll fit the training data, the model to the training data. So the syntax remains same. We'll use the same algorithms from by using the function glm, and we'll use the same data S market, except the fact that we'll subset it only to train. Okay, so we'll subset it to train. Now that's important to remember, because when you're using subsetting, it will take only that subset of data. That means it is going to take only data from 2001 to 2004. The 2005 is going to be excluded from the data set. Okay, because that will be kept for holdout purpose. So let's run this model. So run this now. Let's do the prediction. Now remember, last time around we had done the prediction on the same data, on the full set of data. But now, since we have divided data into two groups, training and testing data, we'll use the test data to do the prediction. Because what matters to us is the error rate or the misclassification error in the test data, not on the training data. Because test data is not part of the training data, and test data is totally different. Now the idea is, or the intuition behind this way of classifying data into two groups is because your model should perform well in completely new data or completely new observations, something that has not been realized or not been seen. Okay, and given that we actually do not know about the future, we just consider that we just take a subset of the full data and consider that or assume that data to be completely new and do the prediction on that data and see if the model is working fine or not. So here is when we do the predictions, let's see what is the percentage of correct prediction. So we'll use the same way, the way we did last time around to get the confusion and accuracy, confusion matrix and the accuracy ratio. But this time we'll do the confusion matrix with the test data, not with the training data. Remember this thing. Okay, we have got the test data, not the training data, not the training data or even the full data. Last time around we had done it with the full data, I remember. Now this time we have got different results. So let's see what exactly is the accuracy. So 44 times both predicted and actual are up. 77 times the predicted and actual are down. So let's see what exactly is the accuracy. So accuracy is nothing but the correct prediction divided by the total number of observations. The total number of observations is 252 and the correct prediction is 44 plus 77, and that comes out to be 48%. Now 48% is very bad, isn't it? Because it is doing worse than what one would be getting by simply tossing a coin. So with just random guess, you will get a success rate of 50%, whereas with this model in place, it is doing nothing better. It's just doing worse than what you will get in random prediction. So that's one bad thing about using the full data, building for model. Okay, so it's important to use a test data and do the validation of your model in order to be sure that your model is performing well. What is the conclusion from here? Is the model doing well or not? The conclusion is no, it is doing very bad. Okay, the existing or the current model that we have with us is doing very bad job, because it's predicting only 48% of data correctly, and rest it is doing a misclassification or a wrong prediction. But we can improve on this model. We need not have to use the same model that we have built so far. We can do a twist to this model. We can just do a bit of fine tuning with this model, and we can get a better model. So one of the way of improving the performance of a model, a predictive model, is that look at your explanatory variables or the features. We have got 5 lag variables and one variable called volume. Now most of these variables are not doing well. If you look at the results from the summary statistic that I showed to you, many of these lag variables are not very significant enough, or they are not contributing towards the prediction of this model. Now this might be a problem, that it is actually helping, or rather helping adversely, or it is adversely impacting the predictive ability of this model. Okay, so let's get rid of the unwanted or variables that are not so important for the model. So looking at the variables that we have seen in the summary statistics, there are 3 lag variables, and volume are not helping much. They are simply creating more problems. So the high prediction error rate that we have seen last time is probably, and we are not sure yet, probably because of this not so important variables. These variables may be contributing towards the high prediction error. So let's remove them. So the two most important variables are lag 1 and lag 2. So, and intuitively also that makes sense, because stock price movement it doesn't depend much on the higher lags. Okay, today's stock price or tomorrow's stock price will depend on today's stock price and day before today's stock price, not 5 days ago, right? What the stock price was 5 days ago, so that's intuitive as well. So let's go ahead and build the model with just 2 explanatory variables, lag 1 and lag 2, and let's see if the model is improving. Okay, now we'll calculate the probabilities for the test data. So we'll do it for test data because that's what matters to us. And now with the new model in place, the model we hope to produce better result. Let's do the confusion matrix for this. Okay, so we just run the tabulated form for the predicted value and the actual data from the test data. Okay, and remember, we are doing the validation, or we are creating the this confusion matrix on the test data. That's important to remember. Do not do that with the training data. Okay, so we just use the training data for building the model. Okay, so I'm just repeating the same thing over again because many people commit this mistake. They use the trained data for building model and use the same data for validation purpose, and they're happy about the fact that they're getting a good result, which is not to be the case, because that should not give you the confidence. Only when your test data is doing or the model performing very well on the test data, you should be rest assured, otherwise not. So let's tabulate it, and when we tabulate it, we got 106 good correct prediction for moving up, both actual and predicted, and 35 cases where both are moving down. So let's see what is the correct prediction. 106 plus 35, and the total number of observations is 252. Okay, in the test data. So the accuracy is 55.9%, or almost 56%. Now remember, we started with 52% and it came down to 48%. Now it has 56%. So the model has improved drastically by eliminating some of the unwanted variables, explanatory variables. Okay, now this model can be used to sort of predict if the stock price will move up or down based on the given probability from this model. So this is of course not the final model. You can improve on this. You can use more variables. You can use the power. You can use the square of this lag. You can take logarithmic. You can use a lot of transform variables, and let's see whether the accuracy ratio is actually improving by including these transform variables. Okay, so try out, and I leave it to you. Just try with square of lag 2, and take the logarithm, the exponential value, and any sorts of mathematical transformation you can do with these variables. Take the what do you call it as this multiply lag1 and lag2. So just do the experiments yourself and see whether the accuracy ratio is improving or not. It could actually go down sometimes, but we just hope that it actually improves. So just try it out, and thanks for watching, and please subscribe to our channel. Thanks. Hi. In this video, I'm going to show you how to select the best fit regression model using cross validation. Now, if you're familiar with cross validations, you must be knowing that cross validation is used to select the most suitable or the best fit model out of a set of models. The idea behind using cross validation is that your model should not only perform well in the training data set, it also should perform well in the test data set, right? And several test data sets, not just the one that you have taken, but you can actually take many test data sets and see whether that works well or not. So there are several types of cross validation that you can potentially choose from, and we'll see at least two of them here to understand how you can use cross validations to select the best fit model. And we'll show it in the context of using a linear regression and a polynomial regression model. Now this would be very useful for beginner, but those who are very familiar with cross validation, for them it will be a refresher, but may not be of very advanced standard of cross validations. So I would keep it very simple to make sure that it is useful for beginners in statistical modeling. So we'll use a dataset called auto. It's there in R. It's a built-in dataset, and we'll use a library boot where we have the cross validation function with us. Normally when you're doing regression model, linear regression model, you're using the function lm, right? You must be familiar with these functions, but here we are going to use glm instead of lm, which is a generalized version of linear regression, and glm has many other generalized linear models such as logistic regression, probability regression, other forms of regression with different distribution of different distribution assumptions. So GLM has a set of models, and linear regression with normality assumption is just one form of model, right? So GLM function has this cross validation function inbuilt, so you don't have to separately do it apart from your linear regression. So I'm going to use GLM in this case. So the idea is to fit a model which predicts the mileage given the horsepower of the engine of an automobile, and the data that we are using is auto. Okay, all right. So the linear regression model looks like this. The dependent variable or the target variable is mileage, and the predictor is horsepower. Okay, so when you run this, you will get your result in the a variable. Will save it in the variable glm.fit. So the output from this linear regression will be saved here, and then we'll use the function cv.glm. Okay, and I've already said that cross validation function is enabled in glm. That's exactly is the reason why we're using glm instead of lm. So we'll use this function and we'll provide the data set, and we'll provide the model result that we have received in the previous step, and it's going to give us the cross validation result. Okay, and the cross validation that we're going to use this is the leave one out cross validation. Okay, there are other cross validation as well. So we'll see two types of cross validation here. One is leave one out cross validation, and the other one is k-fold cross validations. If you're not familiar with cross validation theory and what the types are, there is a link below in the description section of this video. You're going to get a video on my channel where I have explained about the different types of cross validation that you can use. I've discussed about 4 or 5 of them. Okay, just for you to be familiar with the theory behind cross validations and so on. Okay, so I'm not going to explain what leave one out cross validation, what k-fold cross validation is. If you want, if you're interested, you can look at the video in the description section, which explains everything. So when I'm going to run this code, and once it's done, I'll print the delta value, which is going to give the cross validation error. When I run this code, this portion of the code, I'll get this result here. I've already run this just to save time for us. So the error that I'm getting here is 24.23 and 24.23. So up to 2 decimal points, it's the same. And then I have 151 here, it's 114. So that's again, it's going down. So I have just used a very simple regression model, which does not change much. But if I take few polynomials to test it out, it will be clearer as to which one to be picked. Okay, so here it is more or less same. Okay, so there is nothing interesting about it. You can't have an option of choosing which one of is to be used. But here we are building 5 different models and seeing which one is actually performing the best by doing the cross validations. So for that, we are first creating a matrix with 5 places where we are going to save the error, and then of course in the end we'll print the error. So creating a vector of 5 error terms, that's what it is. And we're using a for loop, which is going to which is going to be used to build different models in each one of these loops, and this loop will increase from 1 to 5. And the idea behind this is that we'll use polynomial function, and we'll use several of these polynomials in the model. So the first model will have only horsepower as the predictor. The second model will have horsepower plus horsepower square, or square of the horsepower. So that's the quadratic terms. Okay. In the third model, we'll have the horsepower plus square of horsepower plus cube of horsepower. So we're not only using quadratic terms here, we're also using cubic terms. And in the fourth model, we'll have the the fourth power of horsepower. In the fifth one, we'll have the fifth power of. So the model actually gets bigger and bigger. The first model has only one term, one predictor. The second one has two, linear as well as quadratic, and the third one has linear, quadratic, cubic, and so on. Right? So we'll see which one of these performs the best when we run this code. So the code here is this, like this. Okay, so this is the code. So the first, we have just created a vector that has just a blank vector. So we're going to save the error terms over here, and we're using a loop here. So it varies from 1 to 5, starts with 1, and then it keeps on increasing by 1 in each step, and the maximum value is 5. And then we are saving the output in glm.fit, where we'll save the output, and the function that we have used glm, same that we have used in the previous step instead of lm. The target variable is mileage again, and we're using polynomial term to ensure that we'll have a polynomial regression. So we're not going to have only the linear terms horsepower, we'll also have the square of it, the cube of it, and so on. Right? So each step is given by this. In the first step, we have I equal to 1. That means the power of horsepower, there is only going to be a linear term. In the second step, I is going to be 2. So we'll have horsepower plus horsepower square. So there will be 2 predictors, horsepower and square of it. Okay, and in the third, it is going to go up. So that's the way it is going to help us build different polynomial. The first one will be linear, and the rest 4, one of them will be polynomial regressions, right? And then we'll save the error terms in the cross validation in the cv.error vector. And when we run this one, so this is the function, that one we have used previous step. So provide the data set and the output that we have saved from the previous. So this step we save the output, and then we are going to get the delta value of them. So every time there is the first one will be the delta, so that's going to have the error terms. And when I equal to 1, it's going to save the error term of the first model. When I equal to 2, it's going to save the error for the second model, and so on. And finally, we're printing the model. I've already run the code for you, and there are 5 different models. As you can see, there are 5 different error terms. The first one is 24.23. So that same error that we received in the first code that we ran, because we only had the linear term there, right? So here also in the linear term, it's the model value is 24.23151. When you use a quadratic terms, the error value goes down significantly. From 24.23, it goes down to 19.24. So that's a good thing, right? Because we want the error to be as minimum as we possibly can have, right? The third, when you use a cubic term along with the quadratic term, the value is 19.33. In fact, it increases, and then it becomes 19.42, 19.03. So once you see, there's a significant drop from linear term to quadratic, so from 24 to 19. But after that, there is hardly any change. There's hardly any change, you can see, right? It's all around 19. So in that case, there is no point using a more complex model having more number of parameters. It's always good to have smaller number of parameters, right? So the best way to go about finalize the model here is that you go with the quadratic terms. So just have 2 parameters in the model. Okay. So the final model in this case, if I would write it for you, it would be the mileage equal to, let's say there are 2 parameters with this the intercept, of course, horsepower plus beta 2, the square of horsepower. Okay, so this is the quadratic term. Okay, so this is going to be the final model which perform the best, because that's why I'm getting the minimum error with probably a very small set of parameters, only 2 slope coefficients, and one, of course we always have a 1 intercept. All right, now that's what we've seen, the leave one out cross validations. Another famous cross validation technique is the k-fold. Okay, syntax remains pretty much the same, except the fact that we're using k value equal to 10. Now remember that leave one out cross validation is just a special case of k-fold cross validation. When k equal to 1, that's nothing but leave one out cross validation. But k can be any number. Okay, not just 1. It can be 2, 3, 10, 15, anything. So we're going to take k equal to 10. Okay, the code remains pretty much the same. We are using the for loop, but we're going to have 10 models in this case. Okay, so we're going to have the first model as linear, then quadratic, with squaring the horsepower and adding the model, then cube, and then 4th power, 5th power, and so on up to 10th power. So previous code we just kept it limited to 5th power. We're going to increase this 10th power. So I was just curious to know whether this is going to improve the model. If at a later stage there is a significant improvement, and you might see that there is hardly any change, but there is nothing wrong in doing this experimentation to find out if at all it actually improves. So let's use the k-fold cross validation. The syntax remains same up to here, except the fact that we are using 10 iteration instead of 5 in the previous one. Okay, and there is slight change in the syntax here in the cv.glm function. We're using k equal to 10, which is an additional parameter to the function cv.glm, and then we're saving the error terms in the cv.error, and when we run this we get the result like this. So this is the result in front of us. So the first one is again 24.18. Then when you use a quadratic term, it goes down to 19.15, significant drop, but then it remains more or less same throughout, and there is hardly any drastic drop in the error value. Okay, there are few cases where it is 18, but that's not 18.9, but that's close to 19, which is not a significant drop. You might consider though, but there will be several number of, if it is a prediction problem, you might go in for these values as well, having these many terms. If implementation is not a challenge, having more number of parameters, more number of factors. But for simplicity, if you are to see, simplicity is more of a concern than slight compromise on the predictive power, then better to go with the quadratic term, because that's what is more or less same with these values, right? So again, there is the conclusion that we're drawing here is that beyond quadratic terms, the model is not improving any further. So having higher order of higher power of the predictor values, which is horsepower, predictor variable horsepower, is not improving the model. So what we have learned here is that sometimes if you add the polynomial terms in our model, the predictive power increases. But if you keep on adding, it need not increase for a very large order of terms. It just could increase for few terms like quadratic, cubic, but may not improve for higher order. So that's one lesson to be learned. And when you do it back and forth, try out few other transformation, not just taking a power. You can take other transformation, do more feature engineering, take logarithm, exponential value, minimum, maximum, and so many other transformation you can take on the variables. Of course, not on this data set. Of course, there are several other data set that you can use and test it out. But the mode of selection of the best fit model using cross validation remains what I have explained below, and the most simple form of cross validation that you can use to select the best model. But ensure that the model is good enough both in terms of having the minimum errors number of minimum error value. At the same time, the models will be simple enough. Having too many parameters is not always recommend, because it's likely to overfit. If you use, let's say here you are using 8 parameters with hardly any significant drop in the error terms, it's likely to overfit. Okay, you're not sure though, but it's likely to do so. But if there is significant drop, let's say it becomes 16, then you might as well go ahead with this. Otherwise, it's better to go with a smaller set of parameters, so smaller set of predictors. That helps. Okay, that helps to not just build and implement, also ensure that it actually works in the real data or the future data, and there is not much of this overfitting issue or lack of performance in the new data. And that's what is the intention of building models, right? Thanks. Hi. In this video, I am going to show you how to perform a decision tree model for regression problem. You might have heard about a decision tree being used for classification, but we can also use decision tree for regression as well. It's not very popular like the classification, but it's nevertheless useful sometimes. And let's learn how to perform a regression model using decision tree algorithm. So before we start with performing the building process, let's first learn a bit of theory of decision tree. So what exactly is decision tree? Well, decision tree is a supervised learning algorithm that can be used for both classification and regression. Oftentimes you use it for classification, but there are instances where you can actually use it for regression purpose as well. So here is a typical example of using decision tree for regression purpose. Now in decision tree, you actually divide your data into subsamples. Okay, and there are various steps in coming up with these subsamples. And in every subsample, to the smallest, smallest of these divisions, you simply take average of the subsample and just assign. So how do we do that. So let's understand through an example, that will be easier. So we're trying to predict the salary of employees. Okay, and we have split the data into two categories in the first in the first step. So categorized in terms of gender, so it's male and female. The second categorization or second split has been on based of whether the job is a tech job or a non-tech job. Okay, so tech job or non-tech. So there are two splits, right? Two different steps of splitting the data. Okay, now somebody male and who is working in tech, we have got three observation in this particular subsample. We have got somebody having 50k, 60k and 70k. So the average of 50, 60 plus 70 by 3 is nothing but your 60, right? So average of salary in this particular node is 60. Similarly, somebody who is male and working in non-tech has average salary of 35. And similarly, somebody with female and working in tech has average salary of 70, right? 60, 70, 80, 70. Okay, and somebody with female and non-tech has an average salary of 45. Now, given this data, somebody who is male, tech, what is its salary? Okay, so given this particular new data to you, you can simply use this tree and find out its salary. Okay, so he is male, so we'll straight away going there. We are at this step, and then he's also into tech, so we are here. So if we are here, the average salary automatically is considered to be 60. Okay, so for the entire subsample falling in that category, you will take the average salary. So average salary would be same for that particular subsample. So that's the way you use a decision tree for regression purpose. Now in classification, you were taking the majority vote, right? Majority vote in these subsample, but that's not the case here. It's the regression problem, so we just average it out. The question is, if this is done so easily, why do we need an algorithm? Why do we need to do it using a statistical software like R? Okay, there are many things actually. It's not that simple. Many times you will face problem with splitting your data into different subsamples. It's very clear over here that we have split it based on male and female, but we wouldn't be knowing how many splits will it have. It could have 3, 4 and many splits, right? Secondly, the problem arises when one of the variable that you have is continuous. For instance, if one of the variable given to use age of an employee, how do you take that into consideration or take that as one of the predictor of your salary for employees. So that is another problem. You cannot split a continuous variable that easily as you can split as you can use a categorical variable. Alright, so for continuous variable, of course, you come up with this a threshold, and based on the threshold you split your data. And to come up with that threshold, you will need some sort of an algorithm. Okay, and that's not easy to just manually go and do it by yourself. Rather, it will take a lot of time, so it's better to go with an automated algorithm, which you can find in many of these statisticals and machine learning softwares. Another problem that you will face is to giving priorities, like which one of these variables will be given higher priority. So why would gender come here? Why not take non-take over here? Okay, so that could be one thing. Why gender over take and non-take, somebody's field of work? Why field of work which is take or non-take is getting lesser precedence over gender? Okay, so that's another thing to be decided in the algorithm also. Alright, so last thing that is important is that how many of these variables or predictors will be used for predicting your data. So that's also important. Okay, so you can have as many number of these predictors predicting your target variable, but then it is going to grow big, and the purpose of having a very efficient model is going to go away because you are having a much bigger model, which is very difficult to explain to someone. And remember, one of the greatest thing about decision tree is that it can well be explained very easily to even non-technical people. And if that is what we are losing out on this, then it is better to go for some other sophisticated algorithm instead of using decision tree, because it has to be kept very simple. So what do we do instead of taking all the explanatory variables, is that we just use what is known as pruning of the tree. So we just make sure that we take only important variables or important explanatory variables in order to build the tree. Okay, and that can well be selected by using what is known as pruning of tree, where you cut the tree at one place and you don't go further. Okay, it decides. So using the pruning algorithm, you decide that what is the optimal way of using your explanatory variable in order to predict the target variable. So these are this um, these are the areas where we will be focusing on, where we'll build the model in R. Okay, so to build the model, I'm going to take the data of is known as Boston data. It's there in the library. I think it's there in Mass library, and library tree is also to be used for decision trees. So you just run the library first, and also let's see what's there in the Boston data, just to understand what data is. So this data is about predicting house price, medial what is that okay, median value of owner occupied homes in. So this is the target variables. It's basically house price, predicting house price, and there are many factors which are responsible for house price for a particular location in the city of Boston in US. Okay, and there are many of them. Okay, I just listed out on this. This is a very popular data. You can find it on the web. So there is crime rate. There is proportion of non-retail business. Then there is tax rate, which also affects house price, and so on. So there are so many of these factors that actually impact the house price. So in order to build the model, let's first do the sampling. So we'll have this training sample in place, and then we'll also have the test sample. So we'll first use the first take this training sample. So how do you get that? We use function sample over here, and that will give us the training sample. That would give us a way to subset the training sample. Okay, that is more appropriate to say. So once that is there, and remember we have taken 75% of the data as the training sample. Okay, so this is the syntax. So if you are not familiar with sampling syntax, so I have just highlighted it for you. Just use sample, and then take the number of rows available in Boston data, and how many of them you want. You just specify here. So I'm just taking 75%. So that's the way I have represented 75% of the data to be taken from the population data. Okay, then we'll fit the model. Okay, so we'll use the function tree, and this is the target variable MEDV, so which is medium. What is that? Is median value of house price. So MEDV, and then I'll use all the factors, everything other than MEDV. So instead of writing all the factors, I just put a dot, and then it is automatically considering all the factors other than MEDV. Okay, the data set that is to be mentioned is Boston, and you are subsetting only for the training. So subset equal to train is also to be used as part of the syntax, and then we'll run this code. Now we have we have trained our model with the decision tree, and okay, have we run it? Okay, fine, yeah. So let's see what's there. Okay, so it gives you what is the root node, how many nodes are there, and you'll also get to know the threshold value used to sort of splitting the data. I was talking about splitting the data when you're using a continuous variable, a continuous factor. You're trying to split. You sort of split the data accordingly with a certain threshold, and that's what it's doing it. So we can also summarize it. We can summarize this, right? Yes. Okay, sorry. So how many variables have been used? So number of terminal nodes is 8. That's what is given to you. Terminal nodes are nothing but the nodes at the end, right? So the example that we gave, there were 4, and here it is like there are 8. You're also given the residual deviance. It's just the it's very similar to what we get mean square error, root mean square error, that kind of thing. Not exactly the same, but it's somewhat similar. So it should be as minimum as you possibly can have. And then the distribution of residual, it should always be 0. Mean should be 0. That's one of the criteria that we should look at. That should ideally be 0. Another interesting thing is that the variables actually used to tree constructions. Remember, we have used all the factors, but the algorithm uses only 3. How many? 3 or 4? 1, 2, 3, 4, 5. Okay, only 5 of these variables have been used to build the model. I guess 6, right? Yeah, 5. So RM, Lstat, dis, nox, and PT ratio. Okay, just refer to the this particular node over here, and you will understand what these variables are. Okay, so RM stands for average number of rooms per dwelling. That's obvious, that matters a lot. Lstat is what? Percentage of lowest status of the population, and so on. So there are only 5 of these variables. So 13 of them have been used in the model, but only 5 of them have been considered or considered to be very useful for the model. Okay, now once that is there, now you understood how the model, how the tree has been constructed. There are a few more things that you need to see. Okay, we learned about optimizing your tree building process, right? You may have just too many factors or too many splits in your place. So how do you know that what is the optimal? You can actually use a cross validation. That's the best way to build a tree. You can go back and forth, see what is the mean square error, test data. If it is very less, go back and rebuild the model, and just build several models and choose the one which is giving you the least mean square error. You can do it manually. You can do step by step, write your own code which will do it for you, and you can do some sort of a repetition of that same thing over many times with different different number of length of tree. Okay, and the one that gives you the least error should be chosen. But then you can also prune the tree, which is an automated way of doing it. Okay. Okay, so before that we'll also plot what we have built, right? So how do we plot it? So we just write plot, and we provide this the variable that where we have saved the summary statistics, and we also use the text and this syntax. Okay, so this is the syntax for plotting the. Alright, so this is the tree that you can look in front of me. That's exactly how we also learned in the slide for the first time. So that's exactly how you can actually beautify it. There are many packages you can use to beautify your model, because if you're using for publication and such thing, you cannot use such a picture. You rather use something fancy or something better looking. All right. The next thing to do is pruning the tree, and we'll use cv.tree function in order to prune the tree, and that's what normally is used in this case. So we'll just use this is for cross validation. So this is cross validation dot tree, and we have provided the variable that has the summary statistics, and we can also plot it. Okay, so let's plot and let's see at what point you have got the list or the best predictive model. Okay, best predictions. Okay, so best prediction is nothing but least deviance or least mean square error. I think it gives deviance. Yes. So in the y-axis you have got the cross-validated deviance, and in the x-axis you have got the size of the model. Okay, size means number of trees, right? Number of nodes that you have. So first, if you do the first split, you have got the highest deviance, right? So that's bad. And as you go on, it is actually going down. But many times you will see, if you go down, the deviance will go down, but it will certainly go up again. Okay, so in that case, you would be choosing let me show you that is better. So many times this picture will look like something like this. Okay, so one should go in for case the tree length exactly where the minimum is. Okay, this is like minimizing the cost function, something similar. Okay, so the deviance should be the minimum. Okay. So here in this case it is constantly going down, so we'll just use 8 as our optimal sort of value. So we'll just prune the tree by taking the best as 8. So this is the syntax of pruning. So prune.fit, I'm just assigning this variable by using prune.tree function, and I'm providing the decision tree statistics to it, summary statistics, and also providing the number of or the length or the size of the tree that should ideally be considered as optimal. Okay. All right. Now let's do that. Okay. Now you can also use summary of this. Okay. Dot fit. Don't change much because we have provided 8 as the terminal node, so it's going to remain same. Had it been less, looking at the diagram that I showed you, right? This diagram, had it been somewhere here, if you use 5, probably it's going to change. Okay, let's change it to 5 and let's see whether there is any change. Yeah. So you can see the number of terminal nodes is 5. So that's what you provide, right, as one of the argument when you prune your decision tree. Okay, now we can also plot it. Yes, so now it's changed, right? Previously it was much bigger, now it is much smaller, right? Whether it has actually increased your model or not, we'll just see by looking at the test error. Okay, so because this is where we only working with the training data, right? But what matters to us is the error rate in the test data, and we can use the remaining 25% because we have taken 75% as the training data. 25% we can just take it out and use this this tree to predict data over there and look at the test error and then decide which one is the better, the original model or the model after pruning, or by just cutting down few of these nodes. So how do you predict? So you can use the predict function. You I have shown it to in any other videos also. You can use predict function, provide the the summary statistics, and then provide the data. We are using test data, which is 25% of the data that we didn't take in the training data. So that's your test data. It's completely new. Okay, and when you run this, you will get this is the predicted value of the house prices for different observations in your data. Now, using this data, you just have to compare it with the actual data. So what you need to do is that take the actual data, and this is the predicted data. You take the difference, which is the error found in each one of these observations, which could be positive or negative. Take the mean square error of that, square them and take the mean of that. So take the root mean square error of that and see if it has actually is actually good enough or not. Okay, and one of the important thing to note here is that you can build several of these decision trees and see which one is giving you the lowest mean square error, and that's the one to be used as the final model. Thank you so much. Hi. In this video, I'm going to talk about the bagging and ensemble modeling. We'll first learn about the theory and motivation behind bagging, and then we will move on to compare bagging model with decision tree and linear regression models. The decision tree is very related to bagging. Bagging is just an improvisation on decision tree. In the last couple of videos, we learned about the drawbacks of decision tree, and we will address the drawbacks in bagging. Okay, so bagging is just combination of decision tree. Before we start, I've just given you just brief introduction of what bagging is all about. Okay, in the third part of the session, we'll just take an example and we'll solve using R. So that is also going to be interesting. We'll see how bagging is able to improve the model accuracy. The last part of the session would be on questions. I'll give you some questions to solve, and if you're able to solve, I encourage you to send it across to me, and then I'll review and get back to you. So let's get started. So we'll start with the theory. Well, we have seen in the last couple of videos on decision tree that a single decision tree doesn't perform well many times. The good thing about decision tree is that it is easy to interpret. It's easy to understand and explain to someone, but it underperforms. And the reason it underperforms is because it is just single tree that is being used. This can be improved. Well, this problem can well be addressed. How do we address this problem? By combining several decision tree. If you are using several decision tree to model the same data, we'll be able to achieve higher efficiency or better accuracy of model. So the way to go about doing is combine several decision trees for the same training set, which would perform better in the test data. So that's the idea behind bagging. Okay, so bagging is just a combination of several decision trees. So that we can say in a nutshell. And how is that happening? Well, when you combine multiple trees, it is going to reduce the variance of your outcome. Okay, so that is how it is able to improve on the prediction ability of the model. Okay, so we can take an example to understand how you can combine observation to reduce its variance. I've got 3 observations, okay, and you can take n number of observations. The variance of each one of these observations is sigma square. Okay, we have got 3 observations, S1, S2, and S3, and the variance of each one of these observations is sigma square. Now, when you take the average of it, S1, S2, and S3, the variance becomes sigma square divided by n, where n equal to 3 in this case. Okay, So it becomes sigma square by 3. That means the variance has come down, right? It has come down drastically by combining or by aggregating, right? So that's what we have learned from the basic statistics, that when you do the averaging, when you average observations, that reduces the variance. Now, in modeling, and you might have heard about what is known as bias variance trade-off. We're concerned about the variance of the result. If you take different data set, you will probably get different predictive accuracy of the model, and the variance could be more sometimes. That is not a good thing. So if the variance is more, then you probably won't have a very good model that will give good accuracy. So the idea is to reduce the variance. So the same technique that we learned here can well be applied in the case of decision tree. Instead of a single decision tree, you can fit multiple decision tree and take the average of the outcome, and then use that as the final model or final model for the training data set. And that's what we call bagging, the technique of bagging. So this is important. We will call it as bootstrap aggregations. So you might have heard about what is bootstrapping. I'll give a very brief idea about what bootstrapping is. Bootstrapping is nothing but sampling from the same sample, taking subsamples repeatedly from the subsamples. Okay, so we have got a sample here, and we are taking smaller samples, overlapping samples, because the same observation could be in different subsamples from this bigger sample. That's known as bootstrapping, taking a subset of the observation, repeated, or rather, the same observation can be in the subsample, so it is replaceable. The observations are replaceable, and taking several samples from this bigger sample randomly is known as bootstrapping. Okay, and that will help us fitting a number of decision tree, because when you have multiple samples, you can fit multiple decision tree, right? So that's the idea. So just keep it in mind what bootstrapping is. And here's an example. We have got a data set of salary and education. So target variable is salary. We're trying to predict the salary of an employee based on the number of years of education. Now we have got let's say 15 observations. So we can take let's say 10 observation at random. Okay, so we can 10 observation from 15 observation randomly, and remember the numbers, the observations can be in different samples, so they're not mutually exclusive, so to say. The observations can appear in multiple samples. So we just take first sample, we call it as T1, and it has got 10 observations randomly picked from this main sample, this one. And we have got second sample T2 in a similar way, and all these observations are replaceable, by the way. And the same observation can be in T1 and T2 and T3 as well. So, and then we took the third sample. Now what we'll do is that we'll fit a decision tree on T1 and a separate decision tree on T2 and another one on T3, and then we will have the the actual value and the predicted value for salary. Okay, the actual values of course is known to us here, and then we'll have predicted value. So we'll have okay, let me show it to here. So we'll have predicted value for model sample 1, sample 2 and sample 3, right? We'll take the average of that and we'll call that as the final one. Okay, the averaging will give a better result. Okay, so the idea is same, except the fact that when you use it in practice, we'll use a different way of doing it. Okay, so it's just an explanation. It's not the way it actually is actually done. There's slight deviation from this one, and we'll see in the next slide how do we actually build. In reality, it's very difficult to take a sample, build a training set, and do the average. So the way we do is take a bootstrap sample or use bootstrapping in order to repeatedly get multiple samples and fit to data. So it's entirely automated, and we will see how it is purely automated way of doing, and we'll use R to do that. So the idea here is to build separate prediction model for each training set. So I've taken 3 training sets in the previous slide, and you can take n number of training sets and fit a separate prediction model. It could be decision tree, it could be linear regression, it could be logistic regression, or any of these models. Mind it, we're not only talking about bagging on decision tree. We can do it for linear regression and logistic regression as well, and we'll then average the result. So this is the 2 step. First, you build a separate model for different training set, randomly selected from randomly taken from the main training set, and then average the result. So you build the model f1x, f2x. These are the different models that you have fit to your data, and you have fit n models to your n subsamples. Then the final model will be just average of that. Okay, so that's why it is called aggregation, bootstrap aggregation, or in short, bagging. Now it can well be used for classification. Now we learned how to do in a regression problem, but in classification the steps would be same, except the fact that instead of averaging you take the majority vote. Okay, pretty similar to how you fit a decision tree. In classification, decision tree is different from regression decision tree, right? In classification decision tree, you take the majority vote instead of the averaging, right? So you take, let's say we have got 3 decision tree, and we have got circles and then squares. Okay, so here the majority is, let's say, circle. Here the majority, let's say, is square, and here the majority is circle, right? So for the same observation, we have got 2 circles and 1 square. Okay, so the final outcome will be taken as the majority one, which is the circle, right? So that's the difference. Okay, you take the majority count or majority vote instead of averaging in the case of classification, but the steps are same. You take random sample and then fill multiple separate models for the different training sets. In reality, it is very difficult to get different samples ready in hand. You'll only get one sample, one big sample, or one population data all the times. So what you do is that you take 2/3, and it's not a thumb rule though. You take 2/3 of the data every time, and then aggregate the result depending on whether it's a regression problem or a classification problem. If it is a regression problem, then you go ahead with averaging it out, averaging the value, or if it is a classification problem, you just take the majority vote. And the above method can well be used for linear regression, logistic regression, and decision tree. However, decision tree is always preferred in this case, but there is no thumb rule as such. You can go and well ahead with linear regression and logistic regression as well, and see if you're by taking multiple samples and multiple models and aggregating them is actually improving on your model or not. The next thing, or the next important thing to know in bagging is how you do cross validation. Normally, if you're building a regression model or a decision tree, you separately do cross validation, right? Build a model on training data and then test your model or validate your model in test data, and you do cross validation in that way, just to find out what is the test error, right? What is the test error? And that's what we are interested in, because that's what we need to minimize, right? So we can do that with out of bag error estimation, and you don't have to do it separately in bag. You can do it on just one go and build the model and then do the cross validation at the same time. So here is we have got sample data, and as I've said, 2/3 of the data is being taken for model building, and it could vary, right? It's random. It could be anywhere. This particular line could be anywhere, here. It could take like if you're taking n number of subsamples, so n number of times you would take 2 by 3 of the sample for model building. So every time you will have 1/3 of your sample as the out of bag or out sample, so to say. So given that you're always using a out sample data in your model, you already have a cross validation done even while you are building the model, right? And that's exactly what is going to be used to calculate the out of bag error or out sample error. So for each observation there would be b by 3 out of bag errors, right? Because each observation would have an out would have one of the section is left out, right? And that section you will have a out sample error, right? And you aggregate that, you take the average of the out of bag error, and that would be considered as the test error, right? And there is no need to do cross validation in this case. You'll get it in one go. And we'll see that when we use R, you'll get the error right away. Then variable importance. This is also important to know. Okay, another important feature of bagging. Now you know that in decision tree, when you are building a decision tree, the good thing about a decision tree is that you know which variables are very important. The ones that are at the top are very important, right? And as you go down in the tree, you will get lesser important variables, right? That's how you rank order important variables in your data or in your decision tree model. But in bagging, you cannot visualize this. You cannot have this tree in place because you are using multiple decision trees. You cannot visualize the way I have visualized this simple decision tree. So in that case, the EG or the advantage of decision tree is now lost. So we have compromised on the interpretability of decision tree just to get a better accuracy. So now there is a trade-off between accuracy and interpretability. Now we have compromised on interpretability because there is no tree as such now, but we have increased on the accuracy. That's what our the motivation, right? However, you can easily get the most important variable from your model. Okay, and how is that done? Well, for a regression problem, you use a matrix called RSS, and for classification problem, you have Gini. And these two matrices will be used to rank order variables used in the bagging model. So once you are done with the bagging model, you can get the most important variables by ranking all the variables used in a model through one of these metrics. Whether it's a classification problem, then Gini would be used. If a regression problem, RSS would be used. Then let's take a case study to understand. So we learned the theory, and one thing to remember is that bagging is just a combination of so many decision trees. That's what you need to keep in mind. That's the only takeaway from the theoretical part. Now let's take an example to understand. We'll take the library ISLR because there is a dataset called car seats. I've used the dataset in the decision tree problem in my previous video. You can watch that video. The link to the video is there in the description section. And then I'm going to load the okay, let me show it to you. Okay, so I'm going to load the package random forest. Well, if it's not installed in your system, just go to packages and then install it first before loading it. And that's the package I'm going to use to build a bagging model. I'm going to take the dataset car seats. So let's see what's there in the data. We've got sales of the car seats, and there are several explanatory variables. There are 10 of them, 10 explanatory. That's the target variable. Sales is the target variable, and it's a continuous one, right? It's a continuous one that you can see. So it's a regression problem, right? It's a regression problem. So we'll try to predict sales with the help of other explanatory variables, okay? Income, advertising, population, and so on. There are 400 observations and 11 variables. Okay, one is target variable, rest 10 of them are the possible explanatory variable. So before we start with the bagging model, let's first build a decision tree model, because we need to compare whether a decision tree, whether a bagging model is actually improving on the decision tree or not. So we'll load the tree library. That's what we're going to use for building the decision tree. So we'll use the function tree, and dependent variable or target variable is cells, and will all the other explanatory variables, like 10 of them, right? And the data set we are using is Rstat, and we have taken 200 observations. 50% of that, we have got 50, right? Total is 50, so total is 400. We are using 200 in the training data set to build the model, and rest for the test data set. And then once that is built, we are predicting using predict function. We are predicting the target variable in the test data, and then the next step would be to find out the root mean square error. How do we find that? We just subtract predict minus the actual target variable from the test data, right? So it's like predict minus actual, and you square them, take the mean of it, take the mean, and you would get the test error rate, right? Test error, and that's the matrix through which you can compare two models, right? The one that is giving least test error is the best model, right? The test rate that we are getting here is 4.7. I'm not going to show you the result from decision tree. You can always try it out yourself. The code is in front of you. All I'm interested in is what is the test error, and that is 4.7. So I need to see if the bagging model is actually improving on that or not. And when I'm visualizing the predicted values and the actual values, I'm seeing this data, and it seems to be not a very good fit. And let's see, because there seems to be higher variance. Let's see if there is an improvement on this or not with the bagging. So let's see if a bagging model is actually improving. You should have been in the previous slide. So first we are getting a training and test data using sample function. We're using 200 observations in the training data set, and in test the rest of the observations are there. So we'll fit a bagging model using the function random forest. The target variable is cells, and we'll use all the variables in place. The data set is Rstat, and we'll subset it for training data set only. And remember, we talked about knowing the importance of each one of these explanatory variables. To know the importance, you have to use what is known as importance equal to true. If you don't want that, you can simply remove this option. Otherwise, just keep it. Okay. Now, once you have run this model, we are seeing what is there in the result. Now, the result shows that the number of variables tried at each split is 3. So we haven't specified how many variables are to be used for split explicitly. It is using 3. Okay, and the number of trees it is taking, that means number of samples. So there are 500 random sample through bootstrapping has been used, and 500 decision trees have been used to do the prediction, and then it has been combined. All that has been automated within random forest function. Okay, so imagine if you do it manually, coming up with 500 random samples from the main sample and fitting 500 decision tree, and then using the aggregation is a daunting task. You just have to use a function which is already doing the entire thing. The mean square residual is 3.21. So what was the mean square error? Okay, so this is on test data, so we can compare. So let's see what is there in the test data. So this is on training data, right? Yeah. So we can't use training data test error, training data residual error for comparison purpose. Okay, so let's do a prediction. So now we have built the model using bagging, using the function random forest, and then we'll use the same statistics which is there in the variable fit to do the prediction, and we'll use the test data, right? Test data is something that is exclusive to the training data, and then once we predict, we'll just plot the actual and the predicted value, and this is what you see. This is much better fit than what you have seen, right, previously. So this is not so good, right? But here you can see it is much better fit, and the variance has come down drastically. You can see it is smaller, right, compared to what we have seen previously. And if you take the test error rate, it is 2.6. So what was the test error rate? Previously it was 4.7. So it is 4.7, right? If I remember correctly, let's go back to the slide. It is 4.7. So the test error rate was 4.7. It has now come down to 2.69. So the model performance has improved drastically because of use of bagging or multiple decision tree to do the prediction. Once that is done, okay, so another thing I forgot to mention you is that you can actually use how many variables to be used. You remember in the previous slide we didn't use how many variables to be used at each split, and by default it took 3. So by using the keyword mtry, you can specify how many variables is to be used, and that could make a difference. You can always try with different numbers, and you would get different results, and the one that gives you the least test error is to be selected finally. Using the function importance and in the bracket, and you use the variable in which you have the model statistics, and you will get the rank ordering of the variables. Okay, and how do you know which one is the best? The one that is that is most important for your model or for your data is going to be selected by two matrices. Okay, one is a percentage of change in the mean square error and node impurity. Okay, so I'm going to explain you what is percentage of change in the mean square error. That means if you remove one of these variable, how is it going to affect the mean square error? So if you remove comp price from the model, it is going to increase the mean square error by 13.70. So it is very important variable, because it is, if you drop that variable, it is going to make the model worse. It is going to bring down the performance by a large quantity, which is 13.7, right? And then another important variable is price. If you drop this variable, the percentage increase in mean square error is 45%. That's a quite big number, so that's important variable. And self LOC is also important, because that is also bringing down the mean square, bringing up the mean square error if you drop that variable. So you can actually plot with respect to the ranks, and it is going to give you, or you can actually interpret better. So this is how the variables have been ranked. The most important variable is this one, followed by price, advertising, comp price, and so on. Okay, so you can use one of these metrics to compare variables. Okay, and that's important because that's one of the lacuna that you have in bagging, that you cannot visualize the model, unlike in decision tree, where it is very easy to know which one of the variable is so important, the one that is at the top. So you use this particular matrix. Alright, now we saw how bagging can be used to improve on the model accuracy. Now this is an assignment, the two simple assignments for you. Assignment 1 is take a classification data. I've taken regression data in the example that I have shown you. Take a binary target variable data, and then use decision tree and bagging to classify the way we have classified and compare the result. Okay, we have done it for regression. I encourage you to do it for classification. The steps would be same. Just build a decision tree, check the test error rate, and then use a bagging model and check the test error rate and compare the test error rate for both these models and see if bagging is improving on the prediction accuracy. The assignment 2 is use a linear regression model for bagging purpose. Instead of decision tree, go ahead with linear regression, okay, and do it manually. Don't use any automated procedure. The way we have used random forest function, right? So fill multiple linear regression model and take average of them. When you do it manually, you probably can't take so many of them. Of course, you can write an automated function by yourself. Just take 10 or 20 models or maybe 50 models, 50 random samples through bootstrapping, and then fit linear regression to each one of them and take or aggregate your result and see if it has improved your model or not. And you can use our email ID to let us know your assignments, and we will review and get back to you with the feedback. Thanks for watching this video. If you haven't subscribed to us, please subscribe, and also please visit the website which is there in the description section of this video. Thank you. Hi. In this video, I am going to discuss the theory behind the random forest model. The course outline for this particular session is as follows. We'll start with the basics of machine learning model. I'll talk about what machine learning models are, and then what are tree-based models. Machine learning models are of many different types. One of the type is tree-based modeling, and we'll see what these models are. And then we'll see what is bagging and random forest. Bagging is a type of model which is very similar to random forest. So we'll do a comparison, and then we'll take an exercise using R where we'll build a random forest model and compare it with other models and see whether it is good or better than the other models or not. And finally, I'll give 2 exercises for you to solve on your own. Okay, so what are machine learning models? Well, machine learning models primarily are of 3 types. Okay, one is supervised learning models, the other one is the unsupervised learning model, and the third type, which is not very often we come across, is the semi-supervised learning models. Most of the times we come across the first type of models, which is known as the supervised learning models. The other two, unsupervised and the semi-supervised, are the ones that we rarely come across. Although in the recent times there is a lot of interest in unsupervised learning, and people are popularizing this model as well. Okay, so what is supervised learning model? Well, supervised learning models are the models in which your data set has a target variable in place. So your algorithm will get to know how the target variable looks like. So here is an example. Okay, you have got y, which is a target variable, the variable that you want to predict using predictors, and there are different predictors, x1, x2 and x3. So using x1, x2 and x3, you are trying to predict y. So the model is able to see in the first hand that how the target variable looks like. Okay, so that is supervised learning. On the other hand, in unsupervised learning, you do not have a target variable. The one thing that you have is your predictors. Okay, so in that case, it is not going to be able to give you which category a particular data point belongs to. All it can give it is only different categories without labeling them. Okay, so this is a label, right? This is the label. Whereas here you cannot label the data. All you can do is simply categorize into different black boxes, that yes, this type, this particular type of data is one type, and there is another type of data. So there is no labeling as such, or there is no target variable as such. So this is unsupervised learning, where the model tries to learn only from the predictors without looking at the target variable. On the other hand, semi-supervised learning is a case where you have a mix of both supervised and unsupervised data types. You have got a target variable for few observations, but not for all observations. Okay, in that case we call that as a supervised learning. So basically in machine learning you will come across these three type of problems. So we'll only be interested in supervised learning, okay, for this video. Okay, so random forest is a supervised learning model, so we'll only take into consideration the supervised learning type of problems. Okay, supervised learning can be of two types. One is regression, the other one is classification. Okay, so regression, I mean, those who are familiar with these concepts, and I'm sure this is very simple to understand. Those who are not familiar, a regression problem is where your target variable is continuous in nature, whereas a classification problem is where your target variable is categorical in nature. Okay, so this is a typical case of regression problem because the target variable is continuous, whereas had it been just 0 1 0 1 or something like that, it would have been categorical, right? So that's classification problem. Now how do you build a learning model? Well, you provide training data and then you build a machine learning algorithm. Using that algorithm, you apply your algorithm to new data which does the prediction. So the idea is and this is primarily for supervised learning, where your training data has your target variable in place. Your learning algorithm learns the pattern or the relationship between your target variable y, which is a function of your predictor variable, right? So that's the idea. You just want to come up with an equation that can be used to predict your new data, right? So that's the idea behind building the model. Now classification and regression problems can be solved in many ways. Okay, you might have come across algorithms like linear regression. Okay, and classification can be done by logistic regression. These are popular and simple linear models. However, we'll talk about a type of model known as the tree-based model. And one of the popular and the most popular tree-based model is the decision tree. Well, decision tree is different from the regression model from the fact that decision tree is more non-parametric in nature, and this is just a jargon. Don't be afraid of what non-parametric is. Well, non-parametric is just that you do not estimate an equation. You do not have alpha, beta, so to say. Okay, in regression, if you're familiar with regression, you have always alpha, beta, right? Intercept and slope coefficients. You do not have such parameters to be estimated in decision tree. All we need to do is just to partition the data and use some sort of a technique to find out what could be the potential value of a particular observation in future. So it's very simple. So here is an example where your x1 and x2 are predictors. So you divide your data based on the values of your predictors, and then you find out what is the final value. The final value, let's for instance, is a classification problem of 0 and 1, and then yes, this group it is 0, and this group this is 1. So somebody falling in this particular group is 0, somebody falling in this one is 1, somebody of this here it is 1. So the idea is simple. You partition your data recursively and then take the majority. Okay, if there are, let's say, 3 0 here, let's say 4 zeros and 2 1s, then we consider this particular segment to be having classified as 0. Okay, let's say we have 3 1s and only 2 0, the majority is 1, right? So the final value is 1. Here in this case we have also majority of 1 and 0 is the minority, so we just took the maximum count and the value is 1. So that's the idea of classifying your data using a decision tree model. If you're not familiar with theory, I recommend you to go through one of my video on decision tree theory, and it's there in the description section. The link is there in the description section of this video. Please go through that video. You will get a better overview. The same thing can well be done for regression problem, except the fact that you do not take the maximum value. Finally, you just take the mean of all the observations. Let's for instance, in this particular segment, there are 4 values: 4, 5, 6, 6 and 6. Okay, so there are 4 values. Okay, so the total is or the outcome is just the mean of the 4 value, and mean is your how long, 21 by 4, which is 5.2. 5 point yeah, it could be 1 or 2, something like that. Okay, so 5 something. So the idea is you can just partition your data and predict the value, whether it is a classification problem, whether it's a regression problem. It's very simple. However, the problem with decision tree models are quite a lot. It's very simple though, but it doesn't capture the nonlinear relationship with your data very well. There are many other problems as well. A decision tree model has a problem of low prediction accuracy and high variance. High variance as in if you change your data, it is the prediction accuracy is going to vary a lot. Okay, so prediction accuracy is going to vary, and that is not a good thing. Not at all a good thing. Okay, so we want models that has less variance, in the sense that if you use 10 data sets, the prediction accuracy should be very consistent across these 10 datasets. It should not vary much. If it varies a lot, then who knows, your model will predict well for your new data or not. That is going to be a problem. So in order to overcome these two problems, we combine many different decision tree and come up with a new tree that is more efficient than a single tree. So we use multiple decision trees. Okay, so we combine the output from multiple decision trees, and that would reduce the variance. That would surely reduce the variance, and we call that as ensembles. Okay, you might have heard ensembles in many other different areas. Ensembles is nothing but combining different pieces of work and then coming up with a really good thing. It comes from the field of music, right? In the field of music, you have many different instruments, like you have drums, you have guitar, somebody is a singer, and then you have tabla player, and then you have somebody playing violin. Well, each one of them is playing their own part, but when you combine them in some sort of way, the combined output is better than the individuals, right? So that is the idea behind ensemble. So you build different models, combine them to ensure that the prediction accuracy is higher than the the single model. So that's nothing but ensemble learning. The idea is to combine weak classifier, a single classifier, a single decision tree. A single decision tree is very weak, Okay, so we need to combine them in order to make them stronger. And there are many ways of combining. One of the way is bagging, the other one is boosting, and the third one is random forest. And that is the topic for this session, where we'll try to understand the idea behind a random forest. We'll not get into the mathematics of behind random forest. So I'll keep the mathematical part as simple as is possible, just to understand the intuition behind random forest model. Okay, so the idea is that you combine multiple decision trees. So instead of just one tree, just have multiple ones. Okay, for the same data. Okay, and then take some sort of an average for all the models that you have built, and you use that. How do you know how many trees to be built, right? You have said many different trees. How many trees? Okay, let's say that value is n. How do you know what is the optimal value of n? How many number of trees is to be created or generated in order to find the best classifier? Well, you just take the, if you're using this model for regression problems, then take the help of square of the error or the mean square error as one of the metrics to evaluate how many number of trees are to be used finally. So what exactly is the value of n? If it is a classification problem, then take Gini index or deviance. Okay, that's the matrix for classifications. So that's how you come up with the optimal value of n. So let's understand bagging first before going to random forest, because bagging is the foundation of random forest. So it's always good to understand bagging first. There is a video in my channel on bagging where I have explained theory and application using R. You can go to that video. It's there in the description section of this video. I'll just briefly explain what bagging is. Well, in bagging is nothing is otherwise known as bootstrap aggregation. Okay, and bootstrap is a very popular technique where you take a subset of your sample randomly. So you have a sample, and there are data points here. You just take a subset of it randomly. Okay, let's say there are 100 observation inside. You just took 60 observation randomly, and you created one sample, sample 1. You take another 60 observation randomly, and you created random sample 2, 3, and so on. That's called bootstrapping, where you randomly picking observations. Okay, but remember, you are picking observation with replacement. That means the same observation can be picked twice. Okay, that's the idea. Okay, let's say you have 100 observations with all unique, like 1, 2, up to 100. Okay, whereas when you're picking observations in your random samples, you can have multiple value for the same number. We can have 2, we can have 4, 3, and so on. So the idea is that the observation should be replaceable, or should be replaced while picking up. Okay, so now you have you understood what bootstrapping is. So bootstrapping is used in bagging. There are 3 different steps we follow in bagging. In the first step, we create bootstrap samples. Okay, and if capital N is the number of observation in your main sample, in the bootstrap sample you will have lesser number of observations. You can have the same number of observations, but good to have a lesser number of observation with replacement. That's the main point to be noted. Okay, so you can have multiple observation from the main sample in your bootstrap samples. Okay, because that's each observations is replaced once it is selected in the sample. So you have multiple bootstrap sample from the main target data or the training data, and then you train learning model, and you can use any learning model, but we'll only talk about decision tree here. So you build decision tree model separately for different random samples. Okay, so if you have let's say you came up with 10 different bootstrap sample, you will build 10 different decision tree model in separately for each one of these data sets. Okay, in the step 3, in the final step, you do the final prediction for this particular data set. Okay, let's for instance you took 3 bootstrap sample. Okay, and this is a classification problem. So the first sample predicted, or the first model predicted that the observation 1 is nothing but it's 1. The second model predicted it to be 1. The third model predicted it to be 0. Okay, so this is observation number 1. Observation number 2 is predicted to be 0, 0, even by the third model 0. Now observation 3 is 0, 0, and then it's 1. So what is the final one? The final for this particular observation, because there are 2 ones, right? So the maximum vote is 1. Here there are 3 zeros, so it's obvious it is 0. There's 2 zeros, only 1, right? So the majority vote is maximum count is 0, so it is 0. So it's the classification problem. Take the majority vote or maximum vote. Okay, right? And remember, the number of models you're using could be a lot more. It cannot be just 3. It could be over hundreds. So that's the idea. Okay. Now, in the case of regression, you just take the average of it. Okay. So if it is regression problem, let's say it's the first model predicted to be 4, and then second model predicted 4, and the third model predicted 5. So the average is 5 plus 4 plus 5 by 3, which is 14 by 3, which is something like 4 point something, right? 4.6. So final value is 4.6. So the idea is you are using multiple models now, the output from multiple models, not just one model. How is random forest different from bagging? Well, in bagging we have used random samples, right? The word random is important because these samples are purely random. It's not something that you have selected on your own. That's the idea. And the idea behind making the sampling random is because the variance is going to be better. There is not going to be overfitting. It's not going to be overfitting. And the variance of the output or the prediction error would be less. Okay, so that's the idea. One of the main difference between bagging and random forest is that bagging uses the full set of predictors. You have 10 predictors, 10 independent variable or predictors. Bagging is going to use 10 of them while splitting your data and while building separate models for this bootstrap samples. However, random forest uses only a subset of them. Random forest uses a random subset of them. It doesn't use the entire set of predictors. It just uses a random subset of them each time. So out of these 10 variables, let's say it selected randomly 6 one of them for first model, another 6 one of them for the second model, and so on. Okay, so the idea is to use the best set of predictors each time rather than taking the entire set. Okay, and that is supposed to improve the randomness. Okay, so we talked about random sampling, but even the variable selection should also be random, right? Variable selection should be random, and that exactly is the main differentiator for random forest with respect to the bagging. So random forest uses a random set of predictors. The random is again, so there are two random things here: random sampling and random selection of variables. So this is even better models on theory. Okay. Now whether this is going to improve the prediction accuracy is something that cannot be guaranteed, but in many cases it is definitely going to improve the prediction accuracy. So question, what is the optimal number of predictors to use? How do you know that 6 variables or 6 predictors is to be used from 10? Okay, so the thumb rule is that if it is a classification problem, then the number of predictors that you should use is square root of k. K is the total number of variables. Say in this case, if it is 10, then you should use root over of 10, which is equivalent to 3. And if it's a classification problem, so if it's a classification, it's a square root of the total number of predictors. If it is a regression problem, it's just the 1/3 of the observation predictors. But you can always experiment. You do not necessarily have to go by this thumb rule. You can experiment with other value of m, other number of predictors, and you probably get a better results. Now bagging is a special case of random forest when m is equal to k, right? Because bagging uses all the variables, right? All the predictors. It doesn't use a random subset of them. Hence, bagging is just a special case of random forest. Random forest uses a random subset of the entire number of predictors. So, when m equal to k, it's just the case of bagging. Yes, so that's what we talked about. There is additional randomness. Not only we have randomness in subsampling or bootstrap sampling, we also have randomness while selecting the predictors, and that will reduce the variance. And it also works well on smaller sample data. Bagging doesn't work well on smaller sample data, whereas random forest has a better performance. So that's another advantage. So what are the steps involved here? Now we understood what the steps involved in bagging. The first two steps in random forest is exactly same as what we have learned in bagging. In the step 1, you select bootstrap samples with replacement from the training data. In the second step, you train the model for each the samples. Decision tree is what is going to be used in this case. So the first two steps are exactly same as what we have learned in bagging. The third step is different, or it's an additional step. Select A predictors out of K predictors. So total number of predictors are available to be K. We are going to take the M predictors randomly, okay, for using for building the decision tree model for these different samples, okay, and that will vary with respect to the samples, okay. Now that's exactly is the difference here, right? This third step wasn't there in bagging, so this is an additional step. When you build a model, you may not use this, there will be default values, and you can always have the control over the default value and see which one is the best one. So prediction purpose is the mean of the for the regression problem, it's the mean of the regression value, and for classification it's the maximum mode. That's what we also have learned in decision tree and bagging. The rule applies, the same rule applies in random forest as well. A few questions you might ask yourselves. How do we choose the splits? The same, it's very similar to what we use in decision tree. We use mean square error for regression, and we use Gini index or deviance for classification. Okay, so these two metrics are used to find out the optimal value, optimal number of predictors to be taken. Okay, how do we select the number of trees? Okay, we talked about number of trees in bagging. How do we select the number of trees in random forest? It's similar, very similar. Okay, you just go on building different number of trees by taking different subsamples or bootstrap samples from the main training data, as long as there is no change in the error. Okay, when there is change in error, you go on building more number of trees. Okay, whenever you see there is no change in the error in your data, then you stop there, because then increasing more or adding more decision tree is not helping improving the prediction, right? So that's where you need to stop. How to select the optimal number of predictors? Okay, so you can try with the default, and then you can increase and decrease and see what is optimal. The default may not work well all the time, so just increase and decrease, do a trial and error, and you might get a better result. So we'll take an exercise and we build a random forest model using R. If you haven't downloaded the random forest package, you should install it first in your system. And once you have installed it, you should load it. First, you should load random forest package. And we'll also build a decision tree model for comparison purpose. We'll also do a comparison of decision tree with respect to random forest, bagging with respect to random forest. Well, for bagging, you don't need a separate package. Random forest can well be used for bagging. So tree is what is going to be used for decision tree model building, and random forest is going to be used for bagging and random forest. And we will use the dataset Boston, which is there in the package mass. So that's what we're also going to load. I'm going to show you how the data looks like. Well, the data, you might be familiar if you have seen my other videos. I have taken this data many times. So the Boston data is a data of housing prices, the median housing prices in the city of Boston, and you have got the target variable as the median value of the house prices. It depends on many other things, the crime rate, the availability of tax rate, and many other variables. Okay, averages of population and so on. Okay, there are 13 predictors. Okay, 13 predictors. This one is the target one. Okay. Now we'll first build a decision tree model. Now decision tree is a single decision tree, right? Single decision tree model. Unlike in random forest where you have over 100 decision trees, it's just a single decision tree. Now we'll see what is the prediction accuracy in this case. Syntax is simple. You are using tree and then target variable, and you are using all the predictors available to you, and the data is Boston. When we're building this model, we are interested in knowing what is the mean square error. Okay, mean square is very similar to the residual mean deviance in this case, and is 13.55. Okay, so that's what the mean square error is. And we compare the different model using this matrix, because the one that gives the least mean square error is the best model, right? So it's 13.55. Just remember that. Now let's go to random forest. Now we can build a random forest using the function random forest, and we have the same target variable, and we're using all the predictor variables. However, we'll use a keyword called mtry, which is going to take randomly 6 out of them. So we have got 13 variables in total, and 6 out of them will be selected randomly. Okay, and that's the essence of building a random model, right? And data we're using is same, Boston. All right. When we run this, we have the mean square error, right? Mean square error residuals is 9.5. So we had 13.55 by a single decision tree. Now we have 9.5. So that has surely gone down, right? So random forest has improved the prediction. Okay, just by having more number of decision trees and averaging, we have been able to improve the prediction accuracy of the model. How many number of trees have been used? 500. If you do not use a number, it is going to use the default value, and the default value is 500. And you can specify how many you want using entry. If you want more, you can use 1,001. It's going to take more time though. Otherwise, you probably get a better result if you're using more numbers. Okay, now we'll do a comparison with bagging and random forest. Now we have seen that yes, random forest is now able to improve on the decision tree. Now the difference between a random forest and bagging is that in bagging, the entire set of predictors is being used. In random forest, there is a random selection of the predictors. So there is double randomness, right? In the randomness. Is that going to improve the model accuracy? We'll just see with this data. Well, we cannot conclude anything, because just by using two different just one data set, we cannot conclude anything. But yes, we can just understand if that improves. We can take many number of data set and see whether that is consistent across different data sets or not. So we'll use the same data set, Boston data, and we'll use the first one is a random forest model because you are using mtry, and the second one is a bagging model. Why? Because the mtry is the total number of variables. We are using all the predictors. Now remember, we talked about when m equal to k, it is nothing but a bagging. A random forest becomes a bagging model, right? So yes, so now we have this bagging model here, and we have got the random forest here. So the only difference is that random forest uses lesser number of predictors, and that uses randomly it takes from the list of predictors, right? Whereas bagging uses the entire set. The mean square error in this case is 9.5 in the random forest, whereas in bagging it is 10.6. So there clearly it's a win, right? Clearly random forest does a better job than bagging. But you cannot predict because the numbers are very similar or very close, right? So you can take different data sets to just verify if that works, but there is definitely going to be some sort of an improvement, if not substantial. Alright, so now we have understood the theory and the application of random forest and bagging or ensemble model in general. Now we have, I'm going to give a few assignments to you. This is the last part of the session, wherein I've been given two assignments. I encourage you to send your assignments to me. You'll find the email ID in the description section of this video. The first assignment is you split the data set into training and test data. Remember, I did not split the data into training and test data. That's ideally should be the way of building model. Okay, so I encourage you to do that, and then compare the test error. We compare the training error. That's not the ideal way to compare two different models. So just see the compare the test error rate for a single decision tree with the random forest model. Now, if you're a beginner and you are not very familiar how to split your data into training and test randomly, and how to compare test error and so on, I highly recommend you to go some of these video in this particular playlist. I have a video on decision tree and bagging. Just go through these two videos, you will get to understand how do you do that. Okay. The second assignment is compare the test error rate for bagging and random for different data sets. So I've taken Boston, right? So you just take many other data sets. We have got a data set called car seats and you can take a data set for classification. You can take a data set of any other data sets like flower data is there, right? All right, so these are the two assignments. The third assignment I would like to give is that we learned it for regression problem, right? You learned it for regression. Now you do it for classification as well. Just take a data set which has a target variable as a categorical data or a discrete one. So use a classification random forest and classification bagging and do the comparison. Okay. Yeah, so these are the three assignments you can do, and send it to me. The email ID is there in the description sections. Thank you so much. In this video, we'll try to understand what is multinomial logistic regression, and where do we use multinomial logistic regression, and how do we perform this type of regression using R. Okay, so you might have heard about logistic regression. I'll just do a brief recap of what logistic regression is all about. It's a type of regression that is used to model binary target variable. And oftentimes the target variable could have values like 1 and 0. Okay, what are the typical examples of logistic regression, or where are the examples where you use logistic regression to build models? You want to find out the default or non-default status of customer's loan. You want to find out whether someone has cancer or he doesn't have cancer, whether somebody is going to survive after operation or he's going to die. So for that kind of a problem, you use logistic regression, which is able to classify data into two categories, right? And then we categorize the data into one, which is event of interest, and 0, which is not the event of interest. All right, so that's logistic regressions. When we add the multinomial to it, we just extend that to multiple values, not just two values. Okay, we also call that as multi-class classification. So this is also otherwise known as multi-class classifications, where we just extend a two-class classification that we do in logistic regression to a multi-class problem. So let's take an example to understand. So multinomial logistic regression takes more than two values. It need not be just 0, 1, 1. It could be 3, 4, 5, and more than that. And the values should not be ordered. And if that is ordered, then we call that as ordinal logistic regression. And we'll see that in a separate session. So the value need not be ordered, and I'll explain why. What do you mean by the values should not be ordered? Well, this is an example. So in this example, we're trying to find out how is different characteristics of a student is related to the profession that he chooses in his life. So choosing profession based on certain characteristics, that's one multi-class problem, or that one problem where we can use multinomial logistic regression. So the target variable can have multiple options, right? One can choose to become a doctor, to become a lawyer, or teacher, or a businessman. We cannot order these values. They're more or less similar. We can order this, right? Similarly, choice of a color like blue, uh, red, yellow, we cannot order them either, right? But we can order certain values, right? For instance, let's say the target variable is like uh, okay, it's like the weight of the income of an individual. Okay, high income, middle income, and then low income. So this is the target variable. The target variable has three values: high, middle, and low. This is also a multi-class classification problem, but we wouldn't be using multinomial logistic regression in this case, where we can order the values in different order, whether it's ascending order or descending order. We will use what is known as ordinal logistic regression. So that is a different type of regression that we'll be learning in a separate sessions. So we'll only take the cases or take the multi-class classification problems where the target variable values cannot be ordered, and that's one example where we have somebody's choice of professions could be doctor, lawyer, teacher, businessman. We can't order these values, and that's why we are going to use multinomial logistic regressions. I'm going to take a very small case study to explain how we do that in R, and how we understand the results from a multi-class classification, a multinomial logistic regression problem. So here is the data. We have got somebody's choice of program in the university. Okay, so there are different programs in the university. So what are the reasons, what are the factors that affect somebody's choice of choosing a particular program? So here is the target variable in front of us. We have got three programs: general, academic, and the third one is vocational. Okay, and this is the distribution. We have got 45 data points on people who have joined a general program in college, academic program 105, and 50 people have chosen vocational programs. What are the factors that affect somebody's choice of different programs in college? So that's the problem, right? We have got three classes. So we'll go ahead in using multinomial logistic regression. Now remember that these three classes cannot be ordered, right? We have values like general, academic, and vocational, so we can't order them in any way. These are something that cannot be quantifiable, and we cannot order them in ascending or descending order. And we have got several factors: somebody's gender, socioeconomic status, somebody's ability to read, write. We're not going to use all variables. We'll just take few of them in order to understand a multinomial logistic regression and able to understand the output from it. We've also got variables like ability or score in math, science, and so on. Okay, so what are the choices that we have apart from multinomial logistic? Well, we of course should go ahead with a multinomial logistic, but we also might think that can't we use normal logistic regression, the binary class problems? Well, that won't be suitable here, right? In that case, we might have to do two logistic regression to be able to do somewhat okay modeling, but that's also difficult to interpret and even use it for predictions. It's quite difficult. The third one is the ordered logistic. Now, ordered logistic cannot be applied here. There are certain assumptions associated with ordered logistics, proportional odd, and so on. But that's something that we will take it in a detailed manner in a separate session. But one thing I can tell you is that it's not a very appropriate technique here, because the values cannot be ordered. We can use multinomial probit model, and that is often used in academic literature, where the only difference between multinomial logistic and multinomial probit model is that the error terms is assumed to be having a normal distribution in probit model, in contrast to logistic regression where this assumption is not there. Okay, so the distribution function itself is different in probit model, and if that assumption is valid, then you can go ahead with multinomial probit. So we'll go ahead with the first one because the topic for this session is multinomial logistics, so we'll go ahead with the first one. So we're going to have some kind of two models here, okay, and both the models results is going to be displayed in just one go. We do not have to estimate twice. So here is the logger of somebody is choosing a program general over academic. Now academic is considered to be the base program or the base value. So out of three values, one is going to be considered as a base value and the other two are going to be compared. So the first program, which is an academic, has been taken as a base value. You can actually tweak this. We can change these to other values also. We can make general or vocational as the base value, or the reference value also. But by default it takes the first one, which is academic. Okay, so we're trying to find out the log out of somebody choosing general stream over academic, and the second model is about the log out of someone choosing vocational degree with respect to the academic degree. Alright, and that's a linear function of different parameters. We've got two factors, two variables, two independent variables. One is the socioeconomic factor, and then the ability to write. Okay, so even on social economic factor, which is a categorical variable, we have got three economic factors: 1, 2, and 3. So one of them is going to be a reference one. So first one is a reference one, and the other two have been compared to that. So you'll of course have two estimates in that case, and we have got B11 and B12. So whenever we have socioeconomic status 2 and socioeconomic status 3, and both have been compared to 1, 2 has been compared to 1, 3 has been compared to 1. Similarly, in the second equation also, which is a linear combination of socioeconomic factor and ability to write, we have got two estimates as well: 2 compared to 1, 3 compared to 1. So that's a typical case of a categorical variable having many categories, where one of the categories considered to be reference category and the other two categories will be compared to that. So of course you have n categories, then you have n minus 1 parameters. So I've got 3, so 3 minus 1 is 2. We have got two parameters, right? Beta B11 and B12, and here also it's B21 and B22. Alright, so with that in mind, let's do the estimation. So in R you can use multinum function, which is present in nnet package. Alright, so the syntax is very simple. Those who are familiar with R programming, for them it's very simple, and those who are not, this is where we are keeping all our results. This is the function, and within function we have got a dependent variable. So this is the dependent variable or the target variable, and this is modeled with two factors or two independent variables: socioeconomic status and ability to write, or score somebody has got in writing skills. And then the data that is going to be used is this one. Alright, so when you run this code, you will get this output. Okay, and when you write the summary of this output, we have kept the output in the variable test. So we'll just summarize it. When you summarize it, you will get the results below. Okay, and what is most important is to understand the coefficients, right? And coefficients have got two types of coefficients. One is the intercepts and the other ones are the slope coefficients. Intercept is, now we need to understand here one typical or one tricky thing here. So if you're familiar with linear regression, you might wonder that there is only one set of equation. But as I've shown, in a multi-class problem or in a multinomial logistic regression in particular, you will have, if you have like 3 classes, you will have 2 equations. You have n classes, you have n minus 1 equations. Similarly, you will get similar 2 results, right? Both from both the equations. In the first equations, You have general, somebody taking the general course in college, the probability or the log out of somebody choosing general over education, and the probability of somebody choosing vocational um, with respect to education. So that's the idea. The first equation that we learned in the previous slide, and the second equations. So I've got the intercept for the first equation and the slope coefficient for the first equation. These are the slope coefficient, and for the socioeconomic status, you will get two, right? When you beta B11 and B12, because there are three classes of socioeconomic status, so you will have two estimates. So you get two estimates here for socioeconomic status middle and socioeconomic status high, and that has been compared to socioeconomic status low. So that is SCS low, and that will not appear in the result. It's a reference category, so that's there in the denominator part. Okay. Alright, similarly for somebody choosing vocation over education, you have the intercept 5.21, and then socioeconomic status middle is 0.291, and this is for socioeconomic status high, and then somebody's ability to write. So that's the coefficients from this regression equations, and we have got the standard error, which gives you, helps you finding out the upper limit and lower limit of these coefficients. As you know, like you need diagnostic statistics in any regression problems. The deviance is a very good diagnostic statistics, and of course the Akaike information criteria, right? You want these values to be as optimum as possible, right? So now when you have multiple models, like you can have more models, then you can always compare the residual deviance and AIC and finalize the model. But that's not the purpose of this session, so we'll not get into the model selection part. We'll rather focus on interpreting the result. So we'll focus on that part. So let's see how we can interpret the results. Now, what is the motivation behind building a regression model? There are two motivations. One is using this as for prediction, and the other one is use it for making inference. Now, there are two different. And of course, in the current world that we live in, both these motivations are always there in whatever problems that we solve, right? And industry, it's equally important to predict something, so that you can automate things by writing a few lines of code, and at the same time you also need to understand the inference, because that way you will be able to understand the relationship between the independent variable with the dependent variable, and that will help in policy making, making better decisions. Now the prediction problem is simple. You given the factors or given the independent variable, you need to predict the choice of the program. If somebody's economic status is known, somebody's score on writing skills is known, one should be able to find out which program the student is going to choose or likely to choose to the maximum accuracy is possible. So that's a prediction problem. And the inference is, how does the factors or the independent variables, such as the socioeconomic status or the writing skills or score on writing skills, affect somebody's admission to a specific program. So we want to know the what do we call as a marginal effect in the second case, right? So marginal effect is like, if we change the socioeconomic status by 1 unit, what is going to be the corresponding effect on somebody's choosing a particular program? So what is the log or a change in the log out of somebody changing choosing a particular program in college? Similarly, we can explain that for other variables like writing score. Alright, so this is what are the motivation behind building a model, and we'll see for both the motivation, how does this model help us. First one we'll see is inference. We'll try to explain how this model can be explained in or rather it would help in understanding the relationship between different variables. Now, given the estimates you have, the logwords of being in general program versus or as compared to academic program. Now these are two programs. The logwords, and those who are not familiar with logwords are nothing but the logarithm of probability of choosing general program, general, by logarithm of probability of choosing academic program, right? So that's logword. It can be transformed to more probability terms, and that will be easier to understand. So the logwords of being in a general program versus in academic program will decrease by 0.533 when moved from SES or socioeconomic status low to the middle. Okay, and how is that possible? Let's go back to the result that I have received. Okay, so from low to middle, you can see the coefficient is minus negative 53328. That means somebody is changing his socioeconomic status from low to middle. His logwords will decrease by 0.533 for choosing a general program over an academic program, right? Slightly complicated to understand, but in a layman terms we can see that yes, from we're comparing somebody choosing general program to academic program, how is going to change? It's going to change by this quantity. So that's what the coefficient of the regression equation means. And what is also important, the sign, right? Whether it affects negatively or positively. The sign of the coefficient will tell us if whether it affects positively or negatively. Similarly, we can also explain like if the logwords of being in general program versus in academic program will decrease by 1.163 when moved from SES low to high, and that's the case. That's the case here. You can see, right? That was nothing but the coefficient of somebody's moving socioeconomic status high, which has been compared to socioeconomic status low. That's why the logword of that happening is minus 1.162. So that's how we explain the inference part. What about the prediction? How do we predict the probability, or rather how do we predict that which program this particular student will join given two information, socioeconomic status and writing score? Now that you can easily find, right? You just use this function fitted and then provide the values. Of course, I have not given, you can use predict also. I've just given the same data set that I've used for modeling, but you can give new data as well. You can provide new data points for socioeconomic status and for writing score, and you can get new probability. But the data that I have used here is from the same data that we have used for modeling. Now for data point 1, you can see the probability of somebody joining academic program is 0.14, and probability of somebody joining a general program is 0.33, and probability of somebody joining a vocational program is 0.51. If you add this 3 value, it should be 1, and it's all case it should be 1. Okay, now take the maximum of this. The maximum of this is 0.51, right? This is the maximum of this. The first student will most likely to join vocational program in this case, and that's what we have been able to predict. So against that candidate, we will say this is vocational. Similarly, for the second one, you see this is also the maximum, right? The third one. So this is also likely to be in vocational. In the third one, it is the academic. The first value is the highest. So this student is most likely to be in academic program. Similarly, you can do that for other things. Like in this case, it is again this one is vocational again, right? That's the way you use this for predictions. How do we use this in real world? In real world, like in business areas, when you're building a model, and that's going to be used for prediction purpose, or rather predicting some values in future. Once you have this clear set of predicted values for the new data, you will implement that in your system by writing a piece of code. But the actual values have been derived from a model, not by hard coding them. It has been, so the insight has come from the model, and then you implement that on a system, right? So that's about predictions. Okay, so I think modeling is not complete without doing visualizations, and you should have done a lot of visualization. We should have done before even building the model. But given that the purpose of this session is more about understanding multinomial logistic regression, we didn't do that. But ideally, one should do a lot of visualization just to understand the relationship, and make sure that you build a model that you understand only after understanding the data. So here is a visualization of the probability scores, and with for different socioeconomic status, and in the x-axis we have writing scores. So this is the probability of getting admission, and then this is the writing score, and we have three graphs for different socioeconomic status, and you will see how is it varying with respect to the socioeconomic status. The first one, this is the red one is the high, the green one is for low, and the blue one is for the middle. So it helps you, some sort of getting a better insight about the distribution of your output, or the probability scores. A few points to note while building multinomial logistic regression. Now, as I've said, in a prediction problem, you cannot use the same training data and validate using the same training data. You have to have a different data set. We call that as a test data set, or holdout data set, or we also call that as a validation data set, which should not be part of training. So if you have 100 observation, make sure you build the model with 70 data points or 60 data points, and validate with the rest 30 data points which are not part of the 70 data points. So always cross validate to ensure that it has a good prediction accuracy, and also ensure that it doesn't overfit. That means it should perform well not just in training data, it should also perform in the test data. Only then the model is good. Otherwise, if that is the case where it does perform well in training data but doesn't do well in test data, then that's an issue, or we call that as overfitting issue. And second thing to remember is that the estimation procedure, or the estimation module used in multinomial logistic regression is the maximum likelihood estimation, MLE, or maximum likelihood estimation. So maximum likelihood estimation requires that you should have a large data sample. Now we don't bother about MLE because the software does it for us. But if the software doesn't do it, we have to write our MLE module and do the optimization by ourselves. So if sample size is not large enough, the MLE's output that we have seen as coefficients such as intercepts and slope coefficients are not going to be accurate enough. So always ensure that you use multinomial logistic regression only when you have large sample size. Thank you so much, and please subscribe to our channel. Thank you. In the last video, we saw how to build a k-means clustering model. We'll see in this video how to build a hierarchical clustering model. So we'll take the same data set that we had taken in the last video, the iris data, which has got data for flowers, the 3 species of flowers. We have got the petal length, petal width, sepal length, and sepal width of the flowers. Now this is a label data, but we're not going to use the variable species. Okay, so those who haven't seen the data, let me show you this data. So it's a very popular data set. Alright, so we've got sepal length, sepal width, petal length, and petal width, and species. Species is the level, but we'll consider as if this data is unleveled, and we'll just remove this variable while building the model, and later on we'll just compare it with the actual cluster. So using the length and width of the flowers, we'll try to find out the correct clustering, or how many clusters of flowers we have. The idea is to find out clusters in the data sets, right? So we'll expect 3 clusters because we know beforehand, but in most real world scenarios you won't know how many clusters are present, so that's slightly more difficult to find out. So one of the big difference, the main difference between k-means and the hierarchical clustering is that in k-means we need to know the value of k, that means the number of clusters present, or we at least think about the data to be present in the data. So we need to know how many clusters could be there in the data. Okay, so that's one big difference. Here in hierarchical clustering, we need not provide the algorithm as to how many clusters we think the data would be having. So that's something that we find it out by running the algorithm, so we don't need not know about it. So that is more exploratory in nature. Okay, this is more exploratory. That means we explore the number of clusters. We also explore which observation belongs to which clusters. Okay, so that's one main difference. The second important thing I'll talk about here is that the way we calculate distance between two clusters. So in the theory section, there is a video in this description section where I've explained how we calculate the distance between different clusters. There are many ways. Two important ways is to take the extreme points to farthest point, and then the other way could be to take the two nearest points and take the distance, and the third way could be take the average distance. Okay, so I've taken the so by default the function that we are going to use hclust, which will do the hierarchical clustering. By default it does complete linkage. That means the way it calculates the distance between clusters is just by taking the the distance between the most extreme points or the farthest points. Okay, so that's by default. We don't have to explicitly specify this. We'll see some other ways also, just for comparison as to which one does a better job. So the function that we will use is hclust, and we're going to have the iris data, and we will take only the first 4 variables, right? Sepal length, sepal width, petal length, petal width. That's why we have done this subset of it. Okay, so let's run this. The second step we'll try to plot, and we will see how many we can consider to be having clusters. So how many clusters do we think that is present in the data? So I've got clearly there are 2 clusters very clear. So this one you can see, the left one and the right one. Out of the below 2 ones, if you see the bigger segments, one of them could be a cluster. Okay, but we are not very sure. 2 is very clear, or 3 also could be one of the case. So we will see 2 and 3. So beforehand we know that there are 3 clusters because there are 3 species of data. So we can go ahead with subsetting it for 3. But in more exploratory analysis, where you do not know for sure how many clusters are there, what you do is that you look at the way the the segmentation has happened, and you only take the ones that is clearly visible to be different. So here you can see a smaller one, so you can take the complete one. Here it is slightly bigger, and you can take this one as one cluster and the other one as another cluster. So that could be 3 clusters clearly. So just by looking at this dendrogram, we are sure that one of the cluster that we expect to be clearly visible in the data is not very visible, and we'll see that just by doing a cross validation. So we'll take 3 clusters out of it, the way we take 3 clusters out of several clusters that we just saw. Okay, so let me show you the plot again, and a few more things to note here, right? So in hierarchical cluster we'll have many number of clusters and subclusters and so on, till the point that each observation is a cluster. So in total we have 150 clusters to be precise. If you have 1000 observations, you will have 1000 clusters. But important thing is to choose from top. Okay, the bigger one will get the higher precedence while selecting the number of clusters. So you have flexibility. Okay, so we'll go with 3. Okay, so the second step is to cut the tree, just to have optimal number of clusters. We cannot have 150 clusters for 150 observations. We'll cut it down for 3. So the function that we'll use is cut tree. Okay, so we now cut it down to only 3 clusters because that's the optimal we believe. Okay, okay, so what's there in the variable? So whatever, so the entire 150 observations are now being clustered into 3 groups. Okay, so if you just make it like, let's say 4, you will see it will be 4 groups. Now you have 1 2 3 4, right? So if you just keep it to 3, then we'll have only 3 clusters, 1 2 and 3. All right, so the next thing to do is to do some sort of a cross validation. Now that's the luxury we have here because the data here is level, but in many situations you won't have that luxury. You won't have a level data to do cluster validation. Sometimes you may not have a complete or a large set of level data, but you may have a small set of level data. Even there you can do the cross validation. That's also a good way of knowing whether clustering is perfect or not. So we will do a cross validation by taking the predicted cluster and the actual cluster. The predicted clusters is there in the variable cut. The actual clusters are present in the iris species, right? So it's iris data. We have this variable species which has got the 3 different types of species. So you do a tabulation of that and see what's the result. Well, you can see that all Setosa 50 out of 50 have been correctly classified. The Virginica, 49 of them have been correctly classified. 1 out of them is not very correctly classified. Versicular is the one which is getting affected the maximum. That means there is a large classification error, which is close to 50% classification error that's happening in Versicular. Only 27 have been correctly classified, 23 have been incorrectly classified. So that's a clear issue. As we are expecting, one of the cluster that we were expecting to be very clear is not very clear here. Even on the dendrogram we saw that's not clear. So we can try other linkage methods, like the way distance is being calculated between 2 consecutive clusters while doing the merging. Okay, so we will take the average linkage method. So we'll make very small change to the syntax. So the syntax remains same except the fact that we have now used method equal to average. Okay, so in that case, instead of a complete linkage which takes the distance between the two extreme data point in the clusters, in the 2 clusters, while calculating the distance, here it will take the average distance of all data points with the corresponding data points in the other cluster. Okay, so for a better understanding of what these linkages are, I have a detailed explanation in the video in the description. You can watch that video on clustering. You will get a thorough overview of what clustering is all about and what the different linkages are and so on. So okay, so let's run this. Okay, then we will plot. So here we have slightly a better clarity, right? We can clearly see here that there are 3 clusters. One is here, this one, the leftmost one, and the rightmost one we have got 2. This one, if you can see my cursor, and the third one, this one, right? So we clearly have 3 clusters. This is a better dendrogram. So this seems to be working better than the complete linkage. So we will cut it down to 3 clusters. All right, and the next thing we'll do is we'll tabulate it. So we will tabulate the actual data with the predicted data. So the actual data is there in iris species, the variable species, and we have the predicted one in the variable cut. So now we see that all 50 Setosa have been correctly classified, 50 versicolor have been correctly classified, Virginica is having an issue. Now we are facing a different issue, right? So previously we used to have a correct classification of Virginica, mostly a correct classification. 49 out of 50 got correctly classified, but Verticular had a problem. We had almost like 50% error rates. But here, Citos and Verticular have been well classified, but Virginica is having an issue. But the error rate is much less. It is somewhere around maybe 30%, 25%, 30%. So depending on which category is more important from a classification point of view, we'll choose which one to go with. Okay, and there are many more methods also. We have only taken down the two ones. You can try out other methods as well and see which one is working fine. One of the thing to keep in mind while building clustering model is that to try out as many clustering models that you possibly can try. You can also try k-means clustering and see which one is working the best. Okay, because cross validation is a big issue in clustering. That's why it's always good to try out as many possible models and do the comparison in some way or the other. In this video, I am going to show you how to build a principal component regression in R. And before that, we'll learn the theory behind principal component analysis, and then principal component regressions. Now, those who are familiar with principal component analysis, they must be knowing that it's a dimension reduction technique, and it's used to reduce the number of variables in your data, or to reduce the dimension in your data. So let's first see what's the theory behind principal component regressions. Well, the idea is very simple. Instead of going ahead with the original set of variables or features that is available to you, to reduce the set by using principal component analysis, and then the principal component that you get out of principal component analysis is then to be used in the regression analysis. So instead of using the original variable, you are using the derived variable, or which are also known as principal components. So that's the idea. So it's basically a dimension reduction techniques, as I have already said to you. So it combines features. Now, how does it combine features? It combines features in such a way that the variation in your target variable is explained properly. So in a linear regression framework, let's say you have y equal to beta naught plus beta 1 x1 plus beta 2 x2. So this is a linear regression, and there are two independent variables, right, x1 and x2. Now principal component analysis will do in such a way that, or will combine x1 and x2 in such a way to come up with a single variable, so that the variation in y that was explained by x1 and x2 will also be explained to the same extent or to similar extent by the combined variable. Okay, let's for instance it combined to be g1, which is some sort of a linear combination of alpha 1 x1 plus alpha 2 x2. Okay, so this is some sort of a linear combination, and then g1 would be replacing x1 x2. So that's the idea, right? And the idea here is that the variance that is being explained by x1 and x2, because that's what is the intention of building a regression analysis, that your independent variables or predictors should be able to explain the variation in your target variable y, and that's what is going to be done by g1 to similar extent what x1 and x2 were doing. Okay, so that's the idea of combining features to achieve the same result or similar result at least. So in that way, the number of principal component that is going to be used will always be less than the number of features. Okay, so you can have as many principal component as the number of features or predictors. If there are p number of predictors, you can have p number of principal component, but the number of principal components used in the in the PCR regression is always less, and I'll tell you why it is always less. It's because if you are using the same number of principal component as that of the number of features available, then you are not reducing the dimension. You are essentially going ahead with the same dimension. So it's not going to serve the purpose. So what it's actually is recommended to do is that use a very small number of principal components. Okay, let's say you have 7 features and you also received 7 principal components. Then just see how many principal components actually maximize the variance of y, or it actually explains the maximum variance of y. Let's say 3 principal components actually explain 85% of the variation. Then it's always good to go ahead with only 3 principal component instead of 7, because that's what then reduces its dimension, right? And we'll see that with an example and it will be more clear. It's not a feature selection method because we are not selecting features. We are rather combining features to come up with a new feature, which is no way related to x1 and x2. So g1 is no way explained in terms of x1 and x2. It's a composite. It's a composition of x1 and x2, which is different than both x1 and x2. So we are not selecting. It's not a selection method like your subset selection or stepwise selection, so as to say. So that's is one of the main difference between principal component reduction, principal component analysis, which is a dimension reductions, with the feature selection methods. Okay, so the idea here is mathematically what it's done is you have a set of features and then you come up with a set of principal components to be used, and principal components will be less than equal to will be p all the times, and most of the times you will see the number of principal components to be used in the regression would be less than the number of features. Now initially let's say we had 4 variables and we came down to 2 principal components which explains maximum maximum variations. For instance, with all the features, let's say 100% variation was being explained. Now with only 2 principal component, 90% variation has been explained. Okay, so given that 90% is a good enough good enough number, we will rather go ahead with 2 principal component instead of just 4 original variable. Now what is that going to do is that when you reduce the dimension, it is going to reduce the bias in your model. Okay, so what is going to happen is that when you test your model, when you cross validate your model is going to do better in your test data instead of using the original set of variable, and that's one of the main reason why one should go ahead with principal component regression instead of the ordinary least square regression or the linear regression, especially when a large a majority of variations is being explained by a fewer set of principal component. Now that is a condition. That doesn't happen all the times, by the way. It all depends on the data that we are dealing with. If 90% or 80% of the variation is being explained to a very small section of principal component, then it's always good to go ahead with principal component. If large number of principal components are required, then it's as good as using the original set of variables. Okay, so that won't then make any difference to the biasness of the model. So in ordinary least square, you use all the independent variables or all the predictors. In principal component regression, you reduce your principal components to you reduce your original set of variables to a smaller set of principal components, and then use these principal components, which are composite variables, which are nothing but the some sort of a linear combination of the original variables x1, x2, and x3 and x4, and use them as in the regression. So instead of beta 1s, we'll have beta 1 dash, beta 2 dash. So these betas will be different from the original beta. Okay, and this so this is principal component regression, where you are using principal components instead of the original variable. So that's the difference, right? So there are two steps. In the first step, you use PCA to do dimension injection, and the second step, so this is the first step, in the second step you do regression analysis using principal component instead of the original set of variables. So there are two steps, and there is benefit in terms of achieving higher prediction accuracy in the test result, but it doesn't always happen. So PCR is not always recommendable. It's very useful in some cases, and we'll see one such case. Okay, so here is the data set with us. We are going to take the hitters data. We have taken it many times. So we are trying to predict the salary of the basketball players in the US, and there are several predictors, and we'll see if PCR is going to do better than the ordinary least square regression or not. Okay, so in order to build a PCR regression, we'll use the library PLS. If not, if the package is not installed, first install it, and then you can get it onto your session, and then you can use a seed value so that you can reproduce the results. If you don't want reproducibility, then you may opt out of it, but if you want to reproduce the result, you just have to use the seed. And then the syntax for PCR regression is very similar to how you do a linear model. So we are going to use PCR, which is the function which is going to give us the principal component regression output. The target variable is salary of the basketball player, and there are several variables. In fact, you can actually see what the variables are. Okay, so we are going to see what are the variables we have. So we have several variables. You can just take a look at it. There are 19 such variables. Okay, and then we provide the data set. We're going to all 19 variables as predictors. Okay, and then we'll scale it. So what do we mean by scaling? So scaling is nothing but we are standardizing it. Okay, to ensure that the mean is, let's say, 0 and the variance is 1. So that's one way of standardizing. Okay, so we're just taking the mean out and dividing by the standard deviation. Okay, in that way you are taking all the predictor value in one scale. Otherwise there is going to have some scale effect, which is negative or which is going to have adverse effect in the outcome. So always good to scale it. Okay, and then you select the model with cross validations. So what it's going to do is that so the question in front of us is, so how many principal components should ideally be selected in the final model, right? Because remember what I have said in the theory section, that you can have as many principal components as you have the predictor variables. Like we have 19 predictor variables, so we would have ideally 19 principal components, but all principal components are not going to be useful. Only the first few important principal components are going to be very useful. Otherwise it's not going to be very it's not going to be serve the purpose of reducing the dimension, right? If you are using like 18 principal component out of 19, then it's not going to serve the purpose, because that dimension is remaining more or less the same, right? So let's run the regression and then we'll look at the results. So let's look at the result with the summary. So we have 263 observations with 19 variables, and we have a target variable. All 19 variables have been taken into consideration, and then we have the cross validations, and we have the cross validation error rate for one component, for two components, and so on, right? So we'll see when do we achieve the minimum error rate, and that's what we are going to select, right? So the idea is that if your model is doing good enough in the training data, it should also do well in the validation data, right? And what is important, that at what number of principal components we are going to have the minimum error rate.
Now remember, you can build a model with one principal component. Okay, so this one gives you the model with one principal component followed by 2, 3 and so on. And the rule of thumb is that the minimum number of principal component we going to have in the model, the maximum purpose we are going to achieve by using PCR, because the idea is to reduce the dimension, right? All right. Now, having that in mind, so how do we select what is the best one? So we can do a plot actually. Okay. So we'll do a plot which is going to plot the mean square error rate. Okay. So mean square error rate is given for each principal components or each regression, right? So remember this single thing, right? What you can see if you look at my cursor is actually for one regression. So if there are 10-fold cross validation we have done, right? All right. So for each principal components we'll have a separate regression. So first with one principal component, second with two principal component, two top principal components. Okay, top as in with some criteria, something that gives the minimum error rate. Okay, and it keeps on adding more principal components so on, and we'll see if that actually helps by adding more or not, and what is the optimum. Okay, so the idea is to look at what is the optimum. So we'll use a validation plot which is going to plot the fitness statistics and is going to plot the mean square error rate with respect to the principal components. Okay, so here is the mean square error rate, and we achieve the mean square error somewhere here, like somewhere 5 if I am correct, or rather I would say here, right, it would be 19 or 18, right? So if you see 5 and 18 are very close, but when you have 18 you actually do not achieve anything by using PCR, because you might as well use an ordinal least square, right, instead of using a PCR, because we have 19 variables and you have come down to only 18, right? So there is only one reduction and that doesn't serve the purpose. So, but if you look at here at 5, it is more or less the same error rate as that of 18, right? But when you reduce 19 variables to only 5 principal components, you actually reduce the dimension to a large extent. So we would go ahead with 5 principal components. Now the question is, how is that going to be used or implemented? Okay, so when you implement it, you save the results with a seed value, and then you do the principal component every time you use this model to predict something. Instead of using the original set of variables, you first get the composite variables, or what we call them as principal components, and then use that for finding the prediction score, or the whether it's probability score, whether it's actual values, salary and so on. If now here is the intention is finding out salary, so we'll use the principal component to predict the salary. So that's the idea about principal component regression. And one thing that is to be remembered is that only when you have smaller number of principal components doing a great job of reducing the dimension and giving a very low error rate, then it's useful. Otherwise it's not. If we wouldn't have achieved at 5, then there is no point in using it. Okay, there's no point in using 15 or 18 principal components and having getting a low error rate, because that we can always get it through linear regression by reducing few variables and so on.
Let's get started with the practical session. So here we are going to analyze the Twitter data. So I've used my own Twitter data, and let us load the required packages. And set up the Twitter's authentication. This is the code for it, and I've set it up. And here we can search a particular word from the Twitter, and you can extract the Twitter based on these words. So I've given the number of tweets 200, and the language would be in English. So let me search the tweets with the name, with the word India. So I've got all my 200 tweets which is related to the word India. And to analyze it, first I have to convert it into a data frame, and the next process is cleaning the data. So to clean all the specific characters, the unwanted words, the punctuations and special characters, and I have cleaned all those. And now we can see the emotions, that is the sentimental analysis of the word to the tweets which I have extracted. So this is going to be my emotional sentimental analysis, the emotions, and this is the positive 1 times 3 positive words are there, the trusted words, the anticipation, the negative words, joy 67, fear 52, and anger, surprise, sadness, and disgust. So these are the emotions which, and the number of emotions of each words are displayed here according to the tweets which I have extracted. Now we can create the word cloud for it. Before converting into the word cloud, we can remove the unwanted punctuations, the stop words, and convert all the characters text into the lowercase and stemming the documents as we discussed in the PPT before. Okay, then we should convert the text into the term document matrix, that is the document the frequency of words will be displayed there with the frequency of each words, and we are converting into the matrix format. Okay, now you can see some comparison of clouds with the words, with the angry and all these emotion words which we have found before, and a cloud with those words, with those emotional words, and the discussed words, the anticipation words, the angry words, the trusted words, surprise words, sadness, joy, and etc. And then let's create a word cloud with those words extracted from the Twitter, and this is the word cloud which we extracted based on the word world. So these are the words, top words, and then we're converting into the document term matrix as I said before, and we are setting the value to 10, and we're going to apply LD here. So LDA with 10 topics. So we're going to split the document into 10 topics. So before I've initialized K to 10 and I've used the value 10 here. So my document will be divided into 10 topics. See, here the document will be modeled with 10 topics. And we can see with further other few documents which have converted in LDA formats. Now each document contains 10 topics with it. So let us see the topics which covers the Word document, and here you can see 10 topics with each document, that is topic 1 to 4 and 5 to 8, 9, 10, and each document contains the set of words as I told before. And the topic 1 contains about India, yoga and dance and all those stuffs, and topic 2 contains relevant few set of words, and same way the other documents contains 10 words. Ten topics and related words. So in case you want to categorize them, we can use Apply and relate the topic to those document, and this is just to view the top 6 of the assignments. The assignments is the variable where I've stored the categorized topics, and this is the LDA. From here we can analyze words and what the topic is related to and what the document tells about, and all these analyzations can be done using the LDA. And then we can extract the trends of each location, of any locations. So we can use the syntax like available trend locations of. So I would get the trend locations with the trend location code. Okay, so each location will have a specific code. By accessing the code of that required location, we can get the trend of that specific location. So here I've chose Chennai and with its location code, so I'm going to execute it, and now we can see the trending topics from the location Chennai. Here are the locations, and like healthy life, today's International Music Day, and staying healthy, and about some movies, top movies, and few trending topics out there are displayed here. And that's all. And many more analysis from the Twitter can be done using this model. This model, while having the two persons Twitter data, we can analyze their similarities and dissimilarities and extract whatever necessary data that you wanted to gather from it. And these are the few extraction which I have done to show an example of this method.